Good afternoon, guys. We'll wait for 1 minute to copy the files. Okay, good. Let us start. Good afternoon. This is the data wrangling with Kaggle data science competition tutorial. Did you guys get a chance to download the slides as well as the various materials? Any suggestions, any thoughts before we start? Or we are okay? Okay, good. So it is an etude, right? So it is usually, we have the practice material, we have the materials to practice. So, work on the materials. We should be able to, upload a couple of participate in a couple of competitions, etc. So it's focus on the practice. The agenda is it's a simpler agenda. We'll go through the logistics, and we will directly go into a Kaggle competition, the Titanic one, so that way we dive into the competition, go through the paces, submit a few entries, and see how it works. After that, we will go in and we'll think about it. Right? We'll say, okay, what does it mean? How do we evaluate the models? Various things like that we need to think through. It is not just a competition; it's also thinking about the data, about the models, etc. Then there is a break at 2:50. So keep an eye. If I miss it, just let me know. The break is at 2:50 to 3:10. After that, we'll come back. We will continue the model evaluation interpretation about 30 minutes. Then we'll go to, there is another competition, the data science and scikit. That's an interesting one as well. We'll go through that competition. And then the third one is the ASUS PAKDD 2014. That's also interesting. I think we'll finish up to that much. By that time, it'll be like about 4:20, something like that. We can, questions, discussions, etc., and then complete the thing. Any suggestions? Anything other that just raise it, because I think it's a smaller crowd. It's a good thing that way, right? We can learn from each other, as well as if we are doing things, we can do it together. That kind of stuff. Yeah, go ahead.
Yeah, I had a quick question because so could you, maybe you're going to do this in your slides, and I don't want to interrupt anything, but could you talk about what Kaggle is?
Oh yeah, that's actually the first one. Yeah.
Okay.
Good. Excellent. In fact.
An account because it was for the prerequisite, but
No, absolutely. Excellent. In fact, so that is the first. In fact, that is the first slide. Excellent. So we'll go through and ask away questions. Our goals and assumptions. The goals are to get familiar with the mechanics of data science competition. The second one is to explore the intersection. Right? It's not just submitting to a competition. It's about the models and various other things, as well as discuss the various things about data science, all kind of stuff like that. At the end of the tutorial, you should have submitted at least 3. We can do more. I have actually talked to Kaggle and increased the number of entries to 10 for all of the competitions. I think the last one it is infinite. So that way we can submit multiple things. Because they had, I think, 2 for one and something like 5 for another one, which was too small for us, right? So that way I asked them for 10, and thankfully they gave 10. Anyway, that is that one. You can read the thing. The close encounters, right? The first is this tutorial. I'm hoping that this will be a jumping point for you to do more hands-on walkthroughs, and then listen to lectures. I have a set of these are all the versus Coursera and various other lecture pointers that I have in my slides. It will take some time, but it's a good thing to learn through those things and do more competitions. If you get on one or two on any of the competitions, let me know. Right? I'm hoping that we'll get to the first, second, third. Even the first 10 is interesting. Right? I'll come back to. There is a competition going on for Walmart, a data scientist one Walmart. So if any of you got a job in Walmart, I hope I'll get 10% of your salary. Just kidding, but it's interesting. These are very good stuff, right? Because anyway. So let us go through the first one. Just want to get through the preliminaries because I do want to make sure that we are able to submit. Right? That's it. Were you able to download Anaconda? Were you able to get to this one on any of the IPython notebooks? Everything is fine, right? Good, excellent. Okay, thanks. The next one, of course, is the GitHub. Right? Were you able to download the GitHub? I also have the files here, so that at least these things are in place. This is also then that is good. The third one, of course, is to make sure that you have an account in Kaggle, because when you submit, you might, otherwise they won't. And also, I hope that you are able to download the data. I can't put the data in this thing. That's why I didn't do that one. Otherwise, I would have put it in the right directories, because each competition has their own rules. So that's why we have to go in and come on in, guys. Two things. One is, were you able to make sure that you are able to make the IPython work in your machines? That is one. And the second is the account in Kaggle, so that you can submit data. In the worst case, you can always, there are two things. One is we have the interval during I think there is a break in the middle where you can actually do that one if you are not able to do that, as well as you can look up to your neighbors, right? Look to your neighbors to start doing that, so at least. And I will stay after this one if we need to make sure that you are able to submit. One of my goals is to make sure that everybody submits at least 2 or 3 entries to Kaggle. Right? That what happens is many times the submission, right? This is like the first of this thing. Oh, I have to get an account. I don't know how this is doing, right? And then that gives a barrier to entry into these things. Once you get through that one, then you get hooked, right? You put on one, then you get like low rank somewhere. Then you say, yikes, no, I need to figure this out, right? How can I get? Then you are hooked, right? Then you look at some new competitions, etc. And that is where we need to go. So that's why I want to make sure that the barrier to entry, we cross the barrier to entry. This was this thing, right? I saw this one I know actually Anthony Goldblum. I don't know whether he will remember me anymore or not, but but I know him. It was before Kaggle was before. It was a small company, right? So at that time itself, but I had this thing, right? Initially, got to get through this one. You had to submit it. Finally, I was able to do that, and now I can submit multiple places. Good. With that positive note, the thing that you asked. Anatomy of a Kaggle competition. Let us see, what does it mean? So Kaggle, what it does is it hosts data science competitions. So what does it mean? The competition, of course, data science competitions, the competitions of data sets, from various domains. As you can see, there are, the HHP, the Horizon Health something. That was a big thing going on for 2 or 3 years. They wanted to find out about the readmission, right? Patients. What is the probability of people getting readmitted after they are, discharged from hospital? That was so they wanted to find that out. There were many data sets like that. Ford wanted to find out. It was interesting. I think it was about something about the people's. I forgot what it was. So there were a lot of competitions. So these competitions, so the companies give out a data set. Of course, the data sets are anonymized. They are vetted out, right? Because you can't put your hospital patient data set into an outside this thing, right? So it has to go through a lot of vetting. They also most probably, by the way, be careful because they might be adding a lot of noise in the data set, right? So that's an interesting thing. So don't assume that the data set is correct. They might have added a lot of noise in the data set, right? What would you do if you wanted to put a data set out or you want to find something out? You'll say, okay, let me get the data set, let me randomize, put a few more things in, right? All those things like they will do. And so they put the data set out. The data set consists of, you can see that one, right? It's good. The data set consists of three things. The training data set, right? That is the data set by which you can train your models. There is the test data set, that is a submission. So they give you a test data set without the whatever you want to predict, that's not there. So you predict using your models and do the submission. We will do that when you'll see how that works. And they also have a data set for a final evaluation. So those are so it's interesting because even after you got a good rank, for example, you got, I don't know, whatever rank it is, 10 or 15 or of course, anybody in this room would be top 10, right? 10 or 15 or whatever, or 100 or 200, whatever it is. When they do the final evaluation, a lot of people went down in the ranks like 200 or something like that. So it's interesting, right? I will talk more about it. So it's not that even when you have a higher rank during the test, in the final your rank might be lower. Each competition has its own rules, right? Some competitions might say you can't be a team. For example, the Walmart competition. What they are thinking of is whoever is coming on the top 10 or 15 or whatever it is, they are going to hire them as data scientists. So they say you can't be a part of a team, right? And then they said, oh, you should not even discuss on the forums. So it was like the forum was nobody, shh, don't discuss anything. This is Walmart thing, right? Etc. So, some competitions, the ones that we chose, they are more of a public competition, public data, because this is for us to learn about it. And so of course, the competitions are time boxed, right? They have a 3 months, 2 months, 6 months. The Horizon HHP was interesting. It ran for 3 years with quarterly goals as well as yearly prizes, right? Finally, I think they had a 3 million or something like that, the total prizes they will give out every year and that kind of stuff. Come on in. So I'm going to continue, but if you have any questions, we can clear up during the break. There is a leaderboard. There is a I will go through these ones. There is an evaluation function, right? You evaluate the evaluation function for about the efficiency of your model. There is a discussion forum, and it could be private or public. We will go through this one very, very soon. So I will go through the website and will show you, how these things are in there, etc. The 3 data sets that we are working on, that we will work today. There is one, the Titanic passenger manifest. We will go through each data set. We will understand what it is, how the data set is structured, what is it that we want to predict, and how would we do it, etc. The Data Science London Scikit competition, that's interesting. By the way, I don't know whether you notice or not, this picture is from Sherlock Holmes, the movie. I don't know whether remember they were building this bridge, and there are all kind of interesting things, right? He was sitting on the top and all kinds of things like that. Then they have the PKADD, right? There is another ASUS competition. So these are the 3 data sets. I don't know whether anybody remembers this picture. This is from the social network. This is where Eduardo Sovereign is writing that ELO algorithm on the picture. Anyway, just because ELO algorithm is interesting, right? That's where the whole Facebook started. So let us go look at the. Let me do one thing. I'll just go through 2 more slides, and then we are going to get into the Kaggle website and do our stuff, the data set, etc. The Titanic dataset is interesting dataset. The training dataset, it has passenger ID, of course, whether they survived or not. The class 1, 2, 3, their names, the age, the number of siblings, the number of parents, children, the ticket number, the fare they purchased, the cabin. A lot of the cabin is not available in the port they embarked from. So that is the data set. The submission we'll see in detail. Mm-hmm. Go ahead.
That's like if they were in the first class cabin or?
Yeah, 1, 2, 3.
Okay.
1, 2, 3. We'll see more. We'll see, 1, 2, and 3. Then we have the result, of course, submission is, they have up to 891, 892 to 1309, and that's what we need to predict and say whether these folks survived or not. So we will go deep into the data set. So our approach, right? So this is a classification problem, right? The only question we have is the survived is either 0 or 1. So the forums, right? The first thing we should do on any competition is troll the forum, right? The forum and say what are people talking about, because there are a lot of interesting discussions going on, right? And learn from others. Learn from the thoughts, whether it is good or bad, learn from others. Then it also starts the thinking process, right? We will look at it and say, oh yeah, this is what, maybe this is a good idea, etc., etc. So there are a lot of models we need to do, so let us go deep into this one. So what I'm going to do is I'm going to switch this one. Start from it would be good if you also do it with me, right? So this is by the way, the freezing bear, right? That is what GitHub gave me the name. I said, oh, that's a good name for the project. Otherwise, I have no clue what it is. So anyway, I assume you have downloaded the data into this thing. So you can CD into the notebook directory, right? CD into the notebook directory, and then type IPython. So I have a different, even though I have that directory as well, I'm going to go into a different directory because I have a few more other things in there which I might use. I might show. So type in IPython, right? Notebook --pylab equal to inline. Does that make sense? We type this guy in. Theoretically, it should go into this thing. You will see only 1, 2, 3, 4. I have a lot more of this thing in. You will see 1, 2, 3, 4 notebooks. Yeah. Yeah, I can tell you that.
The option's PLAB?
Yeah.
PyLab.
Probably. Let me. No, it is PyLab.
PyLab?
Yep. Is that right?
Well,
yeah.
One place in the slides it showed earlier it said PLAB.
Okay, my mistake probably. Okay.
Way back at the
Okay,
start.
my mistake. It's PyLab. Yep. IPython notebook --pylab. By the way, if we don't have the PyLab inline, I also have this thing which says that is the magic thing. What I say percentage inline something, and then it works as well. Basically, this is for showing the graphs on the web page itself. So that's why inline. And it says the IPython has this magic this thing, right? Percentage. So if you put percentage PyLab equal to inline, I have it in, and it will work as well. Does that make sense, guys? So you're okay? Yeah. Okay. Good. I know. I'm not picking people. I just you're okay. You're able to go in. Just wanted to make sure everybody were able to go in. So let us go to one intro to Kaggle. The notebook one intro to Kaggle. So what I did was this thing will show everything, but let me do. I'm going to be adventurous and say clear this thing up. Yep. Any? Which one? You're able to get to the web page, right? It showed a page, right?
Yes.
And the page would have the IPython notebooks.
Yes.
And then the one to use is the one intro to Kaggle. Just click on that one. So when you click on that one, what it does is it starts that IPython notebook. And the first one, of course, is to run the shift enter. Will run these things. I included this PS util as well. This is the process and system utils. I thought that it will be useful. We are not using for anything, but I thought that was an interesting one because it gives you memory and all kind of interesting things. So later, if we need something else, we can use that one. But we are not using any of those things. So we should see the numpy, etc. Right? So now we go in and then we create two data frames. The training and the test data frame. We are reading the train and the test data from where we have downloaded. Right? If you have downloaded anywhere else, you can change that file, this thing here. So we have the data set. The first thing to look at is, okay, let us look at what does this data set consist of, right? What is the, you can see that it consists of 800 and the passenger ID, the survived, the P class, the name, the sex, the age, siblings, right? The children, the ticket number, the fare, the cabin, and the embarked. One of the interesting things that you note is that there are 891 records, but some of them might not have all the records, right? For example, age, all of the records do not have the age. The cabin is 204. The cabin is not filled in at all, right? So we know that, so let us, the data frame, it has the head command. That gives you, like the Unix head command, it gives you looking at, able to see, how many, just the first 4 records or 5 records, it shows 5 records, it shows and it shows all the things in and it prints in a nice table. The describe is another command. If you look at the describe command, it gives you, of course, some of these don't make sense. Right? It gives you the count, the mean, standard deviation. Passenger ID doesn't make sense; it's a number. But age, etc. So at least we have some idea about the describe. So these are some of the things. When you get a data set, these are some of the commands that you should do first, so that you can take a look at these things and say, what is this data mean? What are the things in the data? That kind of stuff, right? So let us look at the group by, right? Let us look at the group by. See that so the group by, this is an interesting command, right? This gives us a summary. We can see that the females and the males, right? How many survived? So let us actually print some percentages. So what does it tell us, right? It tells us that the survival percentage of females is 74. Right, 74%, and so the thing that we could do, very simple, this thing we could do, right? We can look at it and say, if the gender is female, let us say this person survived, right? That's a simple, very simple this thing, and see what we get, right? So one of the things that, as you will see later, in the Kaggle competition is when you have a data, look at the data set. Try some simple things, right? Try some simple, looking at the data, you might have some simple ideas. Try those simple things and see what kind of things you get, right? So let us look at the test head. We see that this is the test data. How many test data we have? Test.count, we have 418. So let us do a simple model, right? So let us do a simple model. So what we are doing is it's a tiny lambda which says if the sex. So what happened is I was doing this one and I made an error and then I put it the other way around, right? I killed all the females and all the males were survived, right? So let us try that one. Then I said, okay, I'll put that one in and see what it does. So because I'll show you what happens. So we do this guy. Then So the test.head, right? Now you have a survived. So if you see that one, all the males survived and all the females died, right? So let us put this guy in. Then the to CSV command, right? That's a good command. It actually creates the output that we need. So we do the to CSV command, and we can submit this one. So let us go to, how many people reach up to this point?
How many are up to this point?
Okay, good. So you should have this sub01.csv in the directory. Does that make sense, guys? Okay. So then we go to Kaggle, right? We go to the Titanic competition, make a submission, right? We are at the make a submission, this thing. So you go in here. So this thing is in, so go to the notebooks directory, right? Go to the notebooks directory. If we follow this one, it should be in Titanic. This is the, right, the sub01, right? This one. We open this one. So we say, okay, PyCon. Number 1, right? Put some command, whatever it is, right? Put some command and submit. Yep, it works. I think it takes time to yeah, it's calculating, coming, come to terms with your brilliance. I don't think we are that brilliant on this one, because we should get like 0.25 or something like that. Yikes, right? 0.23445, right? No, that's like we are like, we will be ridiculed by everybody else, right? They will say, yikes, what the heck did you do? That is fine, but we are able to submit this one, right? We are able to submit. That's okay. That's fine. We should be able to see, like in life, right? We should be able to see the bottom before we can see the heights, right? So which is good. So if we submit this one, at least we are able to submit it. We are able to, right? It goes in. You get a number back. So let us go back and say, do what we wanted to do first, right? The thing that we wanted to do. Yeah, before that, just look at, just verify, verify that the count, right? So that you know that how many counts were there. All males were survived, right? And females were died, right? That's what we did. So actually, let us do the other one. Let us do the one that we actually wanted to do, right? We wanted to, the gender model, actually we have to say male equal to 0, right? We just flip the thing. So that now let us run this one. Yes, we get the male equal to survived equal to 0, female survived equal to 1. Let us create. It should create sub02, right? Sub-02. Just to check, you should always, before you submit, right? Just check and make sure that we did what we did. Right, we did what we did. Right, we did. It got the female survived and all males died. Right? So at least we know that it happened, and just as a checkpoint. So let us go in and submit this guy. Go up here. Go up here. Oh yeah, because I'm way down there, guys. You need to help me. You need to give me some ideas, right? I'm like way down there in the dump somewhere, right? These guys will look at and say, yeah, you're doing the tutorial and look at your rank. That is fine. So make a submission. Let us do our, we have 9, so good, 10 entries, 9 entries left. Go in sub-0 O2, right? This is a O2 submission. Open this guy. Test 2, right? We don't have to do anything, but if we, it's good to put some commands, right? Put something so that you know what you're doing. At least later you can look at it and say, oh yeah, this is what happened. You submit this one. This is strange, right? This person has got 1.0. That's impossible to get. I have no clue what happened, but that person has 1.0. There is no way we can go beyond that, right? He looked up the list. I know, the list is available. Yeah, I know. It is tempting. I know that the list is available, right? Yeah. But, I looked at it and said, guys, this is terrible, right? Because there is no way we could do anything about it. And anyway, so now we get a decent, at least 0.7655. Of course, there are a lot of other people with 7655. Most probably everybody got the same idea, right? This is like tons of people with this 7655 thing, right? Now we know where they are and how they got there. Right? They killed all the males and they said all females survived, right? That's the. Interestingly enough, as you will see later, right? This is the highest score I got. We tried all kind of stuff, support vector machines and this and logistic regression and everything, and no, this is the best score I could get. So that's terrible. But that's fine. The reason is this, right? That is when you look at it and say, let the data tell the story. Right? There is more to it. Now let me say what kind of things I can get out of this one, right? Most probably, so this might be one thing that you can think over and say, what does it mean, right? Maybe there are some logarithmic things in, maybe there are various other things in. So anyway, so I got 0.7655. It's a good, good. So it gives us, at least it gets us from the dump, right? We are decent, we are among the 100,000 or whatever it is who are the same this thing, but still we have a good rank. If you want to try, right, there are other things you can do, P class, right? You can just say if class is equal to 1, survived equal to 1, right? Or you can put some average of class, all kind of stuff, maybe logarithmic classes. There are various other things you can try, very simple thing, right? Just based on 1 or 2 attributes, you make some inferences and then you can submit, right? So that is one thing that you can do, and let us submit that one and see at least how it works, right? But of course, this is just that's just a simple thing. So let us start looking more deep into it. So first question, I'm going to go here and then look at the heading, right? So look at this one and say what are the fields that most probably have no relevance to that one, right? Any suggestions from this thing?
What was the question?
What are the fields that might not have any relevance to the survival, right? We can't, when you give an attribute and you can't make any judgment based on that attribute. The passenger ID, right? Passenger ID, there is nothing in there. So passenger ID, but we do need the passenger ID. So keep the passenger ID, but we would not use it, right? The ticket number was one that is not relevant. Maybe it is of relevance, who knows? But at least because there are some other people who look at the ticket number and made all kind of. But anyway, for now, ticket number, the cabin. The problem with the cabin is that there is only like 200 of them, right, out of 800. So there is no way we can. If we put the rest of them, it doesn't make any sense for us, right? We can't put a cabin on anything. Embarked, the port embarked. By the way, people did make some inferences based on the port embarked, but I think we will just drop that one. The age, we will drop the age. This is because later you can use the age. We'll drop that one. And the name. By the way, even the name people are used with the last name, first name, people have used the title Mrs., Miss, Junior, all kind of stuff like that, and people were able to make a lot of interesting inferences out of that one. So there are a lot of things we can do. Let us just drop a few of them. Right? The ticket, cabin, because these are all, so we dropped those things, so that's why the drop, ticket, cabin, embarked, age, name, right? And in place equal to true, so that you just drop it in place, and access equal to 1. Access means you apply to every row. So every row, because you apply that one, because you could actually do something on the column as well. You can actually, so this particular, this thing. So, so access equal to 1, or is it access equal to 1 column? No, it's row, because you are applying to every this thing and dropping the columns. Yep. And then always the head. Yep, good. So now it is all these things are gone. So one of these things, right? This is like male and female, right? We need to change that into num. So we just do a lambda. We use a lambda, and by the way, I found this lambda, nice little interesting lambda, this thing, right? It selects 1 or 0 based on whether this is true or not. So I like that. I found it somewhere and I thought, this is beautiful, because it very crisp and clear, right? One line, clean. I like this lambda a lot. It's very simple, right? Especially for these kind of operations, right? If you want to turn something into into a number or ordinal thing, it's an interesting one. You can even do other things. So anyway, so once this one, yes, we got the gender, right? So we created the gender column based on the sex column, right? So the gender is then, and then now we can drop the sex column, and then we got so this looks like a good trimmed data set, right? You have the passenger ID, you have the survived, the class, the fare, and the gender. So let us apply the first one is the cart. This is the classification and regression trees. By the way, after going through this one, I have a set of slides where I go through the, at least some of what does all these algorithms mean. But I just wanted us to first go through the algorithms, right? Try the algorithms on a data set and understand what does it mean, how does it give us, that kind of stuff, right? So and then we can look back and say what did we do and what worked, how did it work, right, etc. So this is how you use it, scikit-learn.tree, decision tree classifier. You create a classifier object, CL of is equal to this thing. So you do this guy. So this is where what we are using so far is pandas, right? But the scikit-learn actually requires numpy arrays. So the dot values gives you those fields and turn that into a set of arrays. So the df train, p class, these are the 4 ones, right? We took the passenger ID out. Dot values, we create the data set. And the target, of course, is the survive, right? That is the result of applying these things. So you create the object, then you do the fit, right? You do the fit, you create the fit. So this never worked for me, the PyDot. This is this Python 1.5.2.0 parser, this thing. So this is going to, I shouldn't say that, it worked now. So this is good. This is the opposite of things, right? Usually when you're doing a demo, it doesn't work. Here it works, so it's a good thing. Anyway, it didn't work most probably because I changed the Python, whatever it is. So the reason we are doing this one is to draw the tree, right? We just want to, we wanted to do the tree, right? These are all, you do the graph viz, and then you do the graph, and then you write to the tree. Good. Okay, good. I don't. It doesn't matter. Even if it doesn't write, I'm okay, because I have that. We have the image. Most probably, it killed the image as well. Anyway, what it does is it creates a tree, right? It creates a huge tree. Even though you looked at the tree, you have the image on your this thing. It creates. Right? It creates a huge tree. And it creates a huge tree based on some criteria. I think it uses the entropy criteria or the Gini. There are 2 or 3 criteria by which it creates a tree. And based on the tree, it can make judgments, right? The tree might be that which class they are in, which, et cetera, right? It goes progressively down. Yeah, go ahead.
So I had an error trying to write the PNG file.
Yeah.
And so did the
Yeah. I think you need the graph viz in there. Yeah.
I think we all have that same error.
This is.
I didn't see he had it too?
Yeah.
Okay. So we have no picture.
Yeah. The reason is you need the graph viz. I have the.
I overwrote it.
Yeah, I know. It overwrote it. Yeah, I know.
Well, now you
Good. Sorry, guys. What happened is I got this machine new, so that way I just installed everything in it. Earlier, I think I had the graph viz. So if you have to install graph viz as well, I will add that one. Let me put a note in there. Anyway, you will see a tree, right? There is a tree will be there. In fact, I think, see, the advantage of not working off of this guy is that I have the tree. Because I'm working off of a different directory, right? This is the tree that it creates. It creates a very, you can zoom into the tree and say it creates a complex tree. We can actually, decrease the complexity by saying number of levels equal to 3, etc., etc. But anyway, it creates a complex tree, and based on the tree, it makes decisions. So let us go back. Go ahead. The tree is, so what it does is, it looks at when you have a data, right? It looks at it and says, is this a class 1, class 2, or class 3? Then it looks at it and says, is this a male or a female, for example? Then it might look at it and say, is the fair greater than 13, or fair greater than 10, etc. So the classifier, what it does is it looks at through all the training data, and then it figures out what is the best tree, right? Progressively making decisions, and based on the tree, it classifies things. So for example, let us look at the tree. In fact, it might be a good one to look at the tree, right? If you look at the tree, the first thing that it asks for is, what does it ask for? The top one, gender, right? It asks for the gender. Then it looks at the gender 0.5, right? 1 or 0, right? And then it looks at the fair. Then it looks at the sibling. Then it looks at the fair again, like that, right? So if you go deep into the tree, you can see that it's a very complex tree. It goes through and says, okay, this is the best. And then it uses the Gini. There is this thing called the Gini index, and there is also another technique called entropy. So it uses that technique to say which is optimize the tree, and that's what it does. And then the class, etc., right? It creates a very complex this thing.
So the optimization is based on what is it trying to optimize?
It is trying to optimize the error. It's called a Gini index. So you can read up on that one. But what it does is there are two things: Gini index or entropy. Basically, what it looks as is if I create this tree. Because it has the data, right? It has the data as well as it has the values. So it says, okay, if I ask this question, this question, this question, this question, will I be able to optimize this one, right? Or if I ask, so it goes through a lot of calculations. So it's called a Gini index. So there is a formula to calculate the Gini index, and it calculates the Gini index for various things and then comes back. Gini index is interesting. There is also a thing called entropy. So if you want to, for example, you can say, okay, instead of Gini index, try entropy. These are various methods to calculate I think it looks at the error basically, the percentage error. So now that we have the tree, right? We got the tree. So let us transform the test data, right? We should transform the test data. We should let us see whether because we wanted to delete the rows that we did we should do the same things that we did on the training data set. We do all the things on the test data set. We find out the male, female, this thing. We create this thing. Something went wrong, right? There is a value error, right? It is expected. Why does it give us a value error, right? It gave us a value error. Let us look at what happened on the test data set. What happened is one of them do not have a fair, right? So one of the fairs have a NAN because even though we have 418 records, we have only 417 fair records, right? So now the question is, what do we do? Right? If we can just let us do the describe on this guy, right? When you do so now you have one value missing from the 418 fairs, right? So this is called the imputing, right? We need to do something about it. There are multiple ways of doing it. One way we can do it is we can just drop that record, right? There is we can just drop the record which says this record doesn't have one field, so let us drop the record. Another way of looking at this is saying, let me put an average in there, right? The average of all the fairs, right? So if you look at average of all the fairs, it's about 35.6. So we can put in that way. The reason we put in the average is because there are other values in that line that we want to use, right? We don't want to throw away records like that. There are also other things we can do. For example, even though not in the fair, there is the age. Remember, so some of them do not have the age. So what people have done, one way to do the age is to just take the average of the age and put it in. So people have done more than that. What they will look at is they will look at remember we are talking about the name. There is a name, has a Mr., Mrs., they have the junior, etc., right? So based on that particular, like Mrs., Mr., junior, etc., they calculate the average. So now what happens is if somebody's age is missing and if it is a Mrs., then you can say average of all the Mrs. and I can put it. And if it is a junior, then I can take an average of all the juniors and putting it. So now it's a lot more better, right? Because so you can do all kind of interesting things on that one. So there is a lot of imputing techniques for doing that one. Building features. Yep, exactly. Yep. That's interesting actually. There's a lot of interesting things we can do, right? But we have to understand the domain. We have to look at it and say, what does it mean, right? And we are still making an assumption. But because there are other fields in that record, we don't want to throw away the record. So we say, well, so here, I'm just putting in 35, which is the average of the fairs, right? It might not be, but at least it is better than nothing, right? Than throwing away the record. So now, when we do the predict, it works. So if you look at the head, yes, we have a we have a better prediction based on a tree, right? It is better than just putting in one based on the gender, right? That's what we think. So this one, I just wanted to see the reason I put this one was we don't need it, but I just put in just saying that what was our old prediction versus a new prediction, right? So these are some of the things I just put in so that when you predicted using one particular idea, and now we are predicting using another idea, right?
How do you use the tree to make predictions?
Good, excellent question. That is that fit call. Remember, we have the predict call here, CLF predict. So, excellent, thank you. This one I forgot. So, in the scikit-learn, every algorithm, right? It is a very pattern. They have the algorithm, the way you use the algorithms, they are almost the same, right? You create an algorithm object, CLF, that is because it's a classifier algorithm. If it is a regression, etc., you create the algorithm object. When you create the algorithm object, you give the parameters. For example, number of trees, the tree depth, all kind of things like that, right? You give the parameters. Then you do a fit. That is a training. So once you create that object, and then you feed that object a set of training values, right? Training values and results. So then the object, that algorithm creates a model. Because this is a tree, this created a tree model. If it were a linear regression, it would have created a straight line model, or if we had given in a quadratic equation, it would have created a quadratic model, etc., etc. Right? And now that it has the object has a model now. Now, when you want to predict something, you give the object the test data, and then it will give you the predictions. So the create the object, you do the fit, and you do the predict. And there is also, as we go down, we will also see how do you evaluate the model, right? There are a few other things. You can get probabilities out of it, all kind of things like that. Thank you. Good. So I should have noted it down. I had it earlier, but I forgot. Anyway, so that is how you predicted that one. So we got this guy. So we create these are all more of a creating this one. We have the O3, right? We have the O3 which says, okay, passenger ID survived, and let us see how the O3 works, right? We theoretically, this should have been a lot better. Again, I have to go all the way up. This is bad. I never thought, what I should have done was I should have worked on this one and made one and it's rank 5 or something, then I could have gone it. Anyway, let us go in. This should be O3 sitting in here. Yes, O3 sitting in here. This is where I wrote that Titanic thing. So submit, this is test 3. So this is that we did all the work, we created interesting trees, we imputed the data, all kind of stuff like that, right? So now let us see what it does. I don't think they have added enough hamsters. 74163. See, after doing all these things, we still didn't do better than 76555. But it's interesting, right? But we did some work. This is a methodical way of doing things. We did, so at least we can be proud that saying, yeah, we did all these things. We thought this through. We thought this through the problem. We did all these things, and we got a result. So that is one. Yeah. Excellent. So the SOAR is comparing to your prediction accuracy. So what they have done, they have given us a training set, and they have given us a test data. The test data doesn't contain the survived or not survived, right? So then that is what we submit. We submit saying the test data 891 to 1309 survived or not survived. So they are just comparing the difference, right? They know the actual whether these guys survived or not. So this is just, I think, our accuracy. It's just a straight accuracy more than anything else. There are other things. Even though I didn't put it in, there are other mean square error, root mean square error. There are various ways of evaluating a particular result. So that is why that 1 comes in. Remember the 1.0. That means they predicted everything was, So that means our accuracy is 74.163 most probably. We predicted 74.163. Thank you. Thanks. Good. Even though I glozed over that one, there are root mean square error. There are various other formulas people use to evaluate a model. So it's good. Not bad. At least not bad for our. It is better than our 0.23, right? that was like our the lowest score. So another model is the random forest. So this thing, what it does is, as you have seen, this creates these elaborate trees, right? It creates the elaborate trees based on the data, right? But what it does is, it's a greedy algorithm. It looks at it and says, every layer of the tree, I will optimize for that particular layer. But that might not give the right algorithm. So I have a few slides on this one. But random forest model, what it does is, in the ideal world, it randomly selects the data, as well as it randomly selects the attributes. The reason is this. If you look at the data, right, we know that the gender, right, is any tree, anybody who looks at it, that data, immediately they will say, you have to split based on gender, right? So what happens is, even if you do it any random way, it will still use, because there are some overriding attributes that are, what do they call it? I forgot what they call. These are these powerful attributes, right? So random forest, what it does is it randomly selects a set of the attributes. So it gives chance to attributes that are weaker in that sense, right? Weaker attributes. So that way, in the end, you will get a better algorithm. So that's a random forest model. In fact, random forest model is one of the good models that you can try. Any classification problem that you get, you should try random forest model. And then random forest model, you have the number of trees. There are various parameters that you can change and play with the parameters. So let us try the random forest model. Again, create the object, do the fit, do the predict, and then we manage it, and then we have sub 04, right? So now we should know. Thank you very much. Now we should know how to do a prediction model, right? You create the object, you do the fit, you do the predict, you manipulate things around, you create a test file, and you're done, right? Then so let us go back to here and submit and see where we are at. It should be the CSV04. CSV04. Open. Test number 4. Submit. So this is like this Mongo algorithm that does random things, and that should be doing interesting things and that kind of stuff, right? It's not going to get us any further, but still, right? It's supposed to be a better algorithm. Guys, we did get better. I moved 140 positions up. So random forest did help. Now I can look down upon all these people who have less than 800 and say, what are these dummies doing? They don't know. I'm just kidding. I'm just kidding. Yeah, it's a random forest. Yeah, not a bad idea, right? You do everything. Anyway, no. At least, it made sense. The random forest is a good algorithm. It did give us, it is the randomness, by the way, that give us this 0.770, right? The earlier when I did this one, it didn't give me this one because it randomly selected things, right? By the way, we have only very few. If you look at our attributes, we have only 3 or 4 attributes. Random forest will work better if you have a lot more attributes. Right? Then it can select random various sets of attributes. This is only 5 attributes. What could it do, right? It's a lot harder for it to make any judgments. Yeah, go ahead.
So I was in the scikit-learn tutorial this morning, and one thing on random forest is another attribute you can add to it, which is the seed for the random number generator.
Yep.
So you can have it be consistently. If you want to try and do something where you're reproducing the same random forest each time you can set the seed you want to use for going through it.
Excellent. That's called, one of the parameters is called random value. You can say random value equal to 0, random value equal to 1, random value equal to 2, and it will work. Excellent. Yep. Good. So, yeah. So it's a good this thing. So anyway, we got 0.770. I'm going to keep this. I shouldn't be doing this because if things blew up, then I'm in deeper trouble. But I'm going to, at least now I have a slightly better, right? I moved up 140 positions, right? Anyway, so you see how it works, right? Now you are able to do more things on that one. Now actually we can use more attributes on that one. We can put multiple things in there. You can put instead of age, you can put buckets, all kind of stuff like that. Right? There are various things that you can do on the data, transform the data into multiple areas, and get more things done. So let us go back. And are we trying anything more? So anyway, so there are so random forest is, then you can also try with random forest 100, I think this is 100 trees. Earlier I think it was 10 trees, etc. You can try that one. Let us go into, so now another algorithm, interesting algorithm is support vector machines. These are a lot more interesting support vector machines. They actually find the hyperplane in a multi-dimensional hyperplane. Very interesting algorithm. The reason I put these 4 or 5 of these things are now, I'm hoping that you would go back and read about the algorithms if you don't know already about them, right? Because these are the 3 or 4 algorithms that you can try. And you can use this as a template if you want to try any data set, right? In a classification data set. These are the 3 or 4 algorithms that you can try first, and then get a feel for it, and then you can start doing more things. So again, let us do the support vector machines. Support vector machines are also very interesting, this thing. So you get the sub 0006. Let us submit that one. And we submit, I still haven't gotten anywhere, guys. So go in here, SUB06, open, and submit. So now you got the picture, right? How it works. You're okay? You're comfortable how to submit? Did everybody submit, or you're okay, or you're okay, right? You were able to submit. At least you were able to.
Does Kaggle have an API so that we can just like make our submission? Right?
I know, no, they don't have an API, but not a bad idea.
Well, that would allow you to like put 10 submissions a day.
Yeah, Kaggle API might not be a bad thought. I will send an email. So I think this gave 74641, right? So it's not a, it's a lesser this thing, and so good, right? So, no, absolutely. Mm-hmm. Yeah, coming up. Hmm?
So then could you take the training set and split
Yeah, absolutely. Coming up. Thank you. Excellent, excellent. That leads up to my next set of slides. I do have a set of slides on cross validation, and we actually will do cross validation on this data itself. So excellent. We have those things coming up as well. This is just the initial point, right? But what I wanted to do in the first section was submit a few times, right? Understand a few of the mechanics of this thing, as well as apply a few algorithms, right? Because we wanted to do this should be a kind of a hands-on, as well as before going into deep into the algorithms, we should say what does it mean, right? Because this is more of a Kaggle competition thing. You'll come back, and we will come back. In fact, do all of those things. Good. So that's where we are at. So it's good. You can try various. This has got multiple kernels: RBF, linear kernel, sigmoid kernel. We can try multiple things, right? You should try multiple parameters and see what happens. So that ends our first section, right? Now we will go into more deeper things and say, what does this mean? How do we add things to it? That kind of stuff. A quick time check. I have no clue, guys, where we should be at this point. So these are all, I have the slides which talk about these things. I think we are in good shape. So anyway, there are a lot of other things that you can try, right? This is called the feature engineering. You look at these attributes and then say, okay, what else can I do, right? There are various things you can do. The age, remember we were talking about the mean age, etc. The mother, family size. There are all kind of interesting ideas, especially if you troll the discussion forums, they have more ideas. So you can put all of these things in, you can try all, etc., etc. So I put in enough. Another thing that I did was at least I put all the links, right? And the notes in the slide set so that you can look at the slide set and you can, do this one. Was it okay, guys? It's fine? Good, okay, good. No, I just wanted to, it's only we are a small set of people, right? So now, let us take it to the next level, right? What does it mean, right? We did a few set of algorithms, right? We got some results, some of them not good, some of them good. So what does it mean? Exactly, in fact, thank you for your question. That's exactly where we are. You have to look at and say, what does all mean, right? So even leaving Kaggle aside, any data science problem, whether it is a recommendation problem or whether it is a linear regression problem or any of these problems, right? We get a data set from a domain, right? A thin slice of that domain. Based on the data set, we do some reasoning, we do some modeling, we do all these things, and we start predicting. How good are we, right? What does it mean, right? So there are a lot of other things that we need to think through. Are we done? We are not, right? There are a few things that, first question you should say is that, first of all, we assume that the data set is random, right? There is maybe not, maybe there is a sampling bias. How many people remember the Truman versus Dewey, right? Do you know what happened here? So this was I don't remember the election date. I'm not that good at history anyway. So this was an American presidential election in 1950s or 60s or something like that. So they actually declared Dewey, right, as a winner. So this is actually Truman the next day taking the paper and saying, right, he says Dewey wins the election, but actually he didn't. He lost very badly. So what happened? Why were people able to predict like this, right? A lot of newspapers, they said, oh yeah, he won, and everybody was happy, but actually he lost by a huge margin. So what happened? So what happened was that there was a couple of newspapers. I should have actually written down. I added this in the last minute. Anyway, the newspapers, what they did was, this was like 1950s or something, right? They used the telephone to call people and say, did you vote for Truman or did you vote for Dewey? Right? And they got Dewey as based on that one, they predicted that one. What was the problem? 1950s, only rich people could afford telephone, right? And they all voted for Dewey. So straight sampling bias, right? If it were now, it would have been a lot easier, right? Even now, maybe not. If you ask in Twitter, you will get a sampling bias of the Twitter folks, right? But anyway, that was a straight sampling bias, right? The newspaper said, oh yeah, let us call a few people. They did all these 1,000 people or 5,000, 2,000 or something like that. They called them, they got this, and they said, done. So anyway, so there is a sampling bias, even when you don't know that there is a sampling bias. So be careful of the sampling bias. Maybe not in Kaggle, but when you are talking about real life, you have to think through and say, guys, how did you get the data? Right? So that is important. The question that we need to ask is, can we assure that another data set from the domain will give us the same result? Remember, we had all this, we did the fitting the model and we did the predicting and everything. Will the model remain the same if they take another data set, another sampling and give it to us? So will our model and the parameters remain the same? So now then the question that you asked, right? How can we evaluate the model? And how can we evaluate the right parameters, right? You were talking about, the random number, the values or number of trees. How do you do all these things? So that is what we will go through on the next set of these things. Model evaluation, all kinds of. There are lot of interesting stuff in there. So just before going that one, let us quickly go through the algorithms just to get a feel for the algorithm. See, I put 230 is 226. Thank you. Good. So I just put these tiny numbers in there at least to say where I am at, right? At least some sense of. But I'm fine, guys. Wherever you want to take it, I'm fine, right? Because this is more of a learning this thing, right? This is just a list of algorithms. You should, if not already, go through and read all the algorithms about, right? The various algorithms support vector machine, decision trees, ensemble methods, etc., etc. So one of the interesting things that people ask is, where does the AI fit in? One of the things that I was doing, so now I am working as a chief data scientist in a startup company. Before that, I was leading the AI and robotics practice at Tata. So I was doing all kind of AI stuff. Interesting, right? So the question is, where does it stop? Then people ask the question, right? What does AI mean? What does machine learning this thing? Any suggestions? Any thoughts? What would you say if people ask, what is the difference between machine learning and AI? Or is there a difference? Good. Let me get some water.
Machine learning is more measurable than general AI. AI passing is what, the Turing test?
No, sir. A lot of things work on AI. AI has a lot more things like feature learning, the Boltzmann machines, etc., right? There's a lot of things happening in AI. People pay billions of dollars. Google paid like $450 or $500 million for a company, but so a lot of things are happening in AI. So anyway, there is a difference, right? You're right. There is a difference. You have a point there. AI is still in the labs, this thing, right? So what happened was that earlier, artificial intelligence was thinking about work like humans, right? Remember all these expert systems and all kind of stuff like that, right? That's what people are talking about, right? And replacing the humans and expert rules and that kind of stuff. Now it has changed into think like humans, right? So the brain and that kind of stuff, right? So it is a slightly different twist to it. In fact, computational neuroscience and applying computational neuroscience into AI and that kind of stuff. So it's an interesting domain. And then, of course, like you were saying, this AI has this winter and the summer, right? It goes through suddenly, AI, everybody is into AI, and suddenly, doom. People will say, no, AI is no good, and things like that, it goes away. So now it is a height, and then it could go down. Still, leaving all these things aside, regression, logistic regression, these things are machine learning, right? Random forest, what we saw. The clustering, these are the supervised and unsupervised algorithms, right? And then there is this cute math. The SVM, the SVD, single value decomposition, the collaborative filtering. What they do is they have all kind of matrix manipulations, eigenvalues, and all kind of stuff like that. It's interesting. So a lot of manipulations they do in the matrix, and you are able to take things out. So I put them under the cute math, this thing, right? It's not a tree. The problem with the second this thing is you can't explain them that easily, right? You can explain a tree, right? Even if it's a complex tree, you can explain it. And finally, you have this neural network, Boltzmann machines, etc. These are the artificial intelligence. I just put it in a box, at least you get a feel for what it means, right? This is another diagram. Again, I just put in so that at least you get a feel for what kind of how do the classifiers work, and what not work, but how are they classified? Right? What kind of different types of classifiers? We will come back to this one. So let us go back into the few useful things to know about machine learning. Right? This is our so the first one is if you torture data enough, it will confess to anything. So don't torture data. Right? It's serious, right? You keep on applying things onto data, you will get, right? It will tell you whatever it wants to tell you. But the problem is when you put it in a real life thing, right? Like when you put it in the test and it won't work. Right? So you should keep away from that. Like for example, when we were looking at the first one, right? Our first algorithm was we looked at the gender and said, okay, fine, we will put particular gender and then people survive, right? That is actually a data leakage. We looked at the test data and then we made some assumptions on that one. That need not be true. Right? If you are looking at something else, right? If you are looking at say recommending books or something, you might look at it and say people who bought this book also bought. Maybe you have something which says people who are of whatever, right? Who bought with Visa credit card bought this book, and so you put that one in. That is only because you see the test data. That need not be true. So be careful on that one. Learning actually is a representation, evaluation, and optimization. That's exactly the question that you asked, right? I saw the learning part, I saw the algorithm part. Is that all what is there? It's not. There is evaluation, there is the optimization, there are all kind of other things that one needs to do. And it's the generalization that counts, right? If you are able to get a training data set, and if you are able to optimize for that one, that doesn't solve the problem because you should be able to generalize it to the domain. Data alone is not enough. That's another thing. You should understand the domain, right? That is one of the fallacies of it's not fallacies, but it's in the domain of data science, right? Data science is not just manipulation of data; it's also understanding the domain. You have to have the domain knowledge to make things, right? And machine learning is not magic. One cannot get something for nothing. That's an important one, right? You should have good data that is connected, data that is expressive. Then only you will be able to do something. You should have the knobs and the dials, right? And that is also important. So when somebody talks about and say, okay, can we make inferences out of this one? You have to look at it and say, yep, but you have to give me the enough power for that. Overfitting has many phases. We will go through a few of these. Intuition fails at higher dimension, right? Be careful because when you have high dimensionality, then you get into a lot more. Theoretical guarantees. There is a thing about probability data structures, right? We should look at probabilities and say, can we do something about it? Feature engineering is key, right? Like we talked about earlier, right? It is not just looking at the attributes, making various things depending on the attributes. More data beats cleverer algorithm. This I like a lot. This for example, Google, right? Google does that one. What they look at is they like algorithms that get better with more data. So what happens? There is a we had the thing is sometimes when you compare algorithms with smaller set of data, one algorithm might come out ahead. So then our tendency is to say, okay, let me go and optimize this one, but that is not the right way to do it. You have to look at it and say, let me put more data in and then see which algorithm comes out better. Keep that in mind. Learn many models, just not one. That is why we looked at multiple models, right? Ensembles, that kind of stuff. Simplicity does not imply accuracy, and of course, correlation does not imply causation, right? The standard story about, right, the ice cream and the crime rate, right? There is this theory which says crime rate, ice cream, right, increases crime rate. If you plot ice cream sales versus crime rate, that is because it's correlated. That doesn't mean it's causal because the summer is the thing in between, right? Because the summer people buy more ice cream and then a lot of people go out, so that's why crime rate increases. It's not because by stopping ice cream you won't be able to reduce the crime. That's the point, right? So correlation and causality, that's an important way to look at because there is you got to be very careful on that one. Anyway, that is that. So the simplest model, right? That is another thing, right? You have to look at and say use the simplest model. that is important because complex models comes with a lot of other things. I will go through this one on another slide about the error and the complexity of the models and that kind of stuff. Check your assumptions. There is a thing called homoscedasticity. That means the distribution of the errors, right? If you look at this picture on the left side, you can see that the errors, this is the residual plot. The errors are also distributed. Here you can see that the errors are not distributed evenly, right? So the models we make will differ. We have to think that through and say, are the errors are also uniformly distributed? The variance of the error, uniform variance of the error. That's the right term. Of course, Donald Rumsfeld was also, I'm sure, I don't know whether you have heard Donald Rumsfeld's speech on this one, right? The known unknowns and the unknown unknowns and this kind of stuff. He has an interesting speak on that one. And that is true, right? So the thing about is, this is what we know, right? The known knowns, right? When you have a test data, when you have a training data from a domain, that is a known knowns. And then there are these unknowns, right? This is what you need to be the unknown unknowns, right? That's what people talk about, right? The outcomes, the scenarios that haven't happened, the black swans, all those things, right? So you need to think through and say, well, what are the other things that I don't know, and how do I account for these things in my model, right? So that's important. That's what you are talking about, right? You can take a data, you can predict a model, but you have to think about that this model is going to live there, and then there are other things can happen. This is an interesting when you think about about data science and predictions, and this is the pipeline, right? You collect, store, and transform. That is the data management part. Even though in Kaggle you get everything in this thing, usually you collect information from multiple sources, you store them, you transform them, then you have the reason and model. Then there is also the visualize, recommend, predict, right? There are multiple areas. And then the explore, that is where you look at data for more interesting things. You should also look at the variety, velocity, and volume, right? This is this big data, this thing, 3 Vs. But there is more than that. There is a content, connectedness, the interface, inference, intelligence. These are all things that one should look at. It's not just the 3 Vs. Anyway, the data science folk knowledge, this is from the Kaggle's, this thing, iteratively explore data. We are doing that one. The tools get a head around the data, right? That is why we do the describe, we do the head, we look at those things, we do all kind of stuff like that, right? Don't overcomplicate. If people give you data, don't assume that you need to use all the data pieces of the data, right? Look at pictures. Make sure that you draw graphs and say, and then history of your submissions. Keep a tab of your submissions. Don't afraid to submit simple solutions. I think we are doing all these things. There is more. Again, carefully read the forms to get others people's mindset, right? That's why you have to troll the forums. Look at the raw data, etc., right? So that is that part. What else? I think these are some of the, I think you can read them through. You have the slides. I'm not going to read them through. So this I like, interesting, right? Data scientist, right? Josh Wills was saying that data scientist is somebody who knows better statistics than any software engineer, right? And better software than any statistics person. It's a good thing. Then Will from Kaggle, he says that's a good thing, but the person who is versus statistics than any statistician and versus software than the software engineer, right? So that's an interesting way of looking at it. So going back, I do have a reading list. These are the papers that you can read through. There are some interesting notes on that one. This is the one that I was talking about. You can, if you as and when you get time, go through these materials in this order. They give you increasingly more and more sophisticated, deeper knowledge on various things. So with that point, let me go into the model evaluation, right? So we did a few models, right? We had one model was very simple model, which said the gender this thing equal to 1, survived, etc. Then we had this complex model of trees and support vector machines and that kind of stuff, right? So which is better? And what are the attributes, right? So when you have a simple model, what happens is the red curve is the actual error that you get from the domain, and the blue curve is the error, the model error. So when you have a simple model, these errors are smaller. You know why, right? Because a simple model won't be able to get all the information in the data, right? It's a very simple model. So that means the error will be high, even for the data that it got. So that is why with a simple model, you can never, you have this error line. But if you have a complex model, what happens is your error line goes down. Right? Because you are able to, because the model is complex, you are able to model it better. But the problem with a complex model is that you need a lot more data to get to that point. So when you look at it, if you have a lot of data, complex models will work. But if you have simpler, if you have less data, simpler models will work. Does that make sense, guys? Or the simpler model, that is the bias, and the larger complex model is the variance, right? The variance and the bias. So that's why you have a you have a balance between the bias and the variance, depending on the data, depending on the domain, etc. So this is more on the thought of that side. So keep this in mind. A high bias is underfitting, and the high variance is overfitting, right? Because you have complex models, you overfit the data. When you have less simpler models, you underfit the data because you haven't even been able. With a simpler model, even the model hasn't yet internalized all the interesting things that it can learn from that data. So what do we do? So how can we get a set of data? How can we make use of that data to effectively, talk about our model evaluation, etc. Right? So one scheme is to partition the data. So what you do is so for example, in the Kaggle you have 891, right? You have 891 training set, right? What you do is you partition the data to because it's a training set, right? For 891 people, you know whether they survived or not. So you partition the data into, say, 80-20, and then you train your model with 80% of the data, and then you can test your model with 20% of the data. That is one way of doing it. Or you can do the k-fold cross-validation, where you actually do is you take the data into 5 parts, and then use 4 parts to test and 1 part to, 4 parts to train and 1 part to test. And then you can do it, you can mix that up. Does that make sense? So the reason is this, right? Then when you do this validation, when you do the test, you can look at it and say, how good is my model? Right? You don't have to go and every time submit to Kaggle, and in fact, there might not be any Kaggle in terms of real life, right? So that is where the partitioning the data and the cross-validation helps. Does that ring a bell? Are you comfortable with that this thing, right? I think this is what they were talking about today morning as well, right? For those of you who attended today morning. So now, even here, we are actually taking all the data, right? So there might be, even when you look at the domain need not be true to this data, right? So what you could do is you can actually sample from the data you got. Sample with replacement. That is because this data might have biases in it, right? So what you do is you treat the data as if it is a domain, and then you sample with replacement. So that way what happens is you are adding more randomness, right? That's what you're talking about, random, this thing, right? That's exactly what it does, right? Because you can do a random over another random, because you don't use all the data, you sample the data from the data you get. And in fact that helps, the bagging, and then you can also average the predictions over multiple models. So these are some of the ways you can increase the effectiveness of your model, right? Then there is also the thing called boosting, which also does a similar this thing. So going back to our random forest, right? The reason the random forest works well is because it does the decorrelation, right? It decorrelates the data. Because it does the random one, the data is no more correlated, right? Because it picks up random attributes, it picks up random rows, and then it creates the trees. And then it creates like hundreds of such trees and then combines them together. So that way, even if the data you get has a pattern, that pattern goes away because of all these random things that you do. So that is why it decorrelates the data, and that is how it becomes more effective. And if you see our result, that's why we were able to get random forest got us the maximum, right? 0.77, something like that. It's what you were talking about earlier, right? The random this thing, and that's exactly what it does. Go ahead. Mm-hmm.
So boosting is when I have like, if I remember correctly, is when I have like a minority set of data. So let's say that we want to represent in the data set more so.
Yep.
Right. How do you determine? I mean, if you know that this is like, for example, like in the case of the Titanic, let's say it was like female, in our set, older female.
Yeah, upper class fields, yeah.
There's like three guys,
yep.
Three of them in the thing. So, but how do you go about determining like what you want to boost?
No, what it does is it boosts the ones that are that gives the maximum errors. So you classify, right? You classify, say you classify using say 100 trees, 200 trees, 300 trees, something like that, right? And then you have 100 trees, right? 100 different trees. And then look at the tree and say, there will be the trees that actually gave you lower performance. And you boost them. Remember, because those trees, remember, these trees use multiple sets of attributes, right? Some might use the gender and the fair. Some might use the class and the fair. Some might use the gender and the class, right? Some might have used ticket number and something else. Right? Just for example, the one that used ticket number and something else. Ticket number is not the right thing, but ticket number and something else has, it predicts less. Because the one uses the gender and the class would predict very well, right? It has like 0.8 or something. This thing has only 0.4 or something. So what you do is you boost that one up. And then do it again. Because what you are doing is that is a weak classifier, right? That's a weak classifier based on the attributes. So now you boost the weak classifiers because even though in your test training data set, right, the gender and the class overrules all other attributes. That need not be the case in the actual actual domain, right? So that is what we are doing. We are trying to say that there would be random things in the actual domain. It might be something else. Right? In this one might be a bad example, but if you look at an example of people buying books or whatever it is, right, or people watching TV, etc., right, you might look at it and say higher income people watch Sherlock Holmes or whatever it is, right, or etc., right. That might be case for a particular zip code, but it might not be the same for some other zip code.
So it's a way to avoid this function bias.
Yeah, exactly. Thank you. So that excellent, good point. So what you do is that is why the boosting talks about output of the output of weak classifiers into a powerful committee, right? You look at the weak classifiers and say, I know that they classified weak, but let me boost their thing up. So anyway, I just wanted to, so at least these are some of the slides which talk about more of this thing. I put in the slides enough so that, the reason I put in enough is so that at least you get an understanding of all these things, right? Read through the slides, and we come back to this slide again, right? This slide should make sense. Now you have the bagging and boosting and how these things do what they do. So let us do the model evaluation. Guys, 250. I had no. it is 250, right? Anyway, good. So, excellent. Murphy is going to strike again sometime later, isn't he? The computer might crash or something like that at some point. I know. It's okay, because now I think we passed right? At least we went through the initial stages, and now we can. So now let us do the cross-validation on the data that we have, right? So let us do this. Let us apply this cross-validation to the Titanic data set. So go back to the good. So this guy is done. So intro to Kaggle, close and halt. This thing is 2 model evaluation. Click on 2 model evaluation. That is next to this thing. Standard with our last time I got into trouble. You think I should clear the output? I'm going to clear the output. So what we are doing. So this is just what we did on that one, right? We loaded the data set, we cleaned up all these things, and we got these values out, right? Just all the transformations that we did to get this data set. So let us do these things, and let us start with the random classifier. So we create a random classifier object. So now, the thing that we are going to do is, first thing we should remember, we are talking about the splitting the data, right? Let us split the data, right? This is all data that we have is this 891 data sets, right? So with that data set, we want to find out the effectiveness of our model. So let us split the data set into, is that 80-20? Yeah, 0.2. So let us split the data set into 8.2. What does that mean? So this is what happened, right? It's split up into train X, test X, train Y, and test Y, right? We have the X and the Y. 80% for training and 20% for testing. So we have 4 arrays. Train X with 891. 891 is all. 7112 and 179. Does it make sense? Are you comfortable with that? I made this diagram yesterday. I thought that maybe this diagram will make it a lot clearer, right? The 80-20, right? So by the way, the way it does this one, yeah, I think it does it randomly. I think it does a. I have done it on my own, and I usually do it random, right? You create a random number of 1 to 891, right? And then you create a random number and pick them up. Because even when you have the data set as a table, there might be some bias in it. So what you do is, out of 891, you randomly select 712, put it as a trained data set, and the rest you put it as a test.
With replacement? Or?
No, without replacement. Excellent, excellent. This is without replacement, right? This is, you take the data set, cut it into two parts. Even this one and the cross-validation, both are without replacement. That is why the people have the algorithms like the boosting and the bagging and etc. with replacement. So that is one level up. Because even when we do a random forest on the 712, the random forest does whatever it does. And if we do an ADA boost on that one, that will do the one with the replacement on the 712. What it will do is it will create trees, right? It will create like 100 trees with taking out of the 712. It might take only like 100 every time, for example, or 120 or something. And that will do with replacement. So you do the partition, right? You do the partition, and then you do the fit. You do the fit for this part, right? You do the fit for the training part, and then you do the predict for the test part. And then say how good did we predict, right? You do the predict, and then the accuracy comes to 0.85. So our accuracy was 0.77, 0.78, right? So it's approximate. So let us hold it there. So at least you got the, right, how it does this thing, right? If you go down, it also does cross-validation in the same way, right? You can do the cross-validation which says, give me 5-fold cross-validation, right? When we do the 5-fold cross-validation, this actually directly, it does the cross-validation, it does the predictions, and it gives you the scores of your accuracy, right? So this is what it did. Let me see whether I can make this picture. Right? This is what it did. in the cross-validation, right? You just say cross-validation score. So it does everything, right? Scikit, because we gave it our classify CLF object, right? We gave the object. So it created this five-fold cross-validation, and then it did 5 times, right? Using 1, 2, 3, 4, and then 5 for predict, then 1, 2, 3, 5, and 4 for predict, etc., etc. And it give you the score for all the 5 of them. And so 0.80 to 0.804. Remember, it can't do that much because we have only very less number of attributes, so it can't do. If we had lot of attributes, this will come out very interesting. So the rule of the thumb people say is that you do a cross-validation, 10-fold cross-validation. Remember, because each time you do the cross-validation, it has to do the whole thing, right? It has to do the fit, it has to do the predict, etc., etc., right? So it takes a lot of time. So let us go back. So anyway, so this is a cross-validation and this is a splitting. Does that make sense, guys? Very comfortable? So we can go through, right? I have all the things in so that, and interesting because we are using the same Titanic data, we can look at it and because the data set is small enough for us to look at it and understand it and say how these things worked. So another thing that we do is the confusion matrix, right? So the confusion matrix is the predicted versus actual, right? If in the Titanic case, you have the 0 and 1, right? People who survived and people who died, right? What you predicted and what is true, right? So this the accuracy would be that. So this is what? This is the true positive, right? You predicted that people will survive and they survived. This is the false negative because you predicted that they will die, but they actually survived. And here, this is a false positive. They actually died, but we predicted that they will survive. And this is a true negative, right? We predicted that they will die, and it did happen. So we can actually, going back here, we can actually print the confusion matrix for our so the confusion matrix for our this thing, right? If we printed this one, this is our this thing, right? This is the actual and the predicted, right? We predict the 96 and 54 hours. Our model was right. 11 and 15, it was wrong. Then there are various things. So there are 2 interesting things on this one, right? The precision and recall. So the precision is how many you identified were relevant, right? You predicted, right? You predicted 1 for these many people. You predicted that they will survive, right? And out of that, only these many survived. These many actually died. So that is the precision. And the recall is on the other side. How many these are the people who survived. How many of them did you predict that they will survive? Does that make sense? The precision and the recall, right? One is, so let us look at it this way, right? This is what, if you are in a legal, what do they call it? The legal, where they go in and search for everything, right? Discovery, thank you. So in legal discovery, is it precision important or recall important? It's the recall, right? It's the coverage that is important, right? You wanted to get all the things, right? That are, because you're looking at discovery, if they are looking at, I don't know, emails, right? Emails which say something, right? You don't want to miss any. Even if you because what they will do is after the discovery, they will go through those emails, right? And then figure out whether these are good, these are incriminating emails or whatever it is, right? It is important that you don't miss any of the incriminating emails. Even if you got a lot of emails that are junk, that is fine because you can go through that one. On the other hand, like they talk about search, right? If you are in a search, is it precision or recall important? It's a precision, right? If you see the first 4 links, and if they are not right, you will abandon that one. right? So that means you want to, your precision should be high. All the things that you identified, they should be right. On the other hand, if it is a legal one, you should identify all the things, even if you identify a lot of this. So anyway, so that is the difference between, precision, recall, and it depends on the domain. So one of the interesting they talk about is a fraud, right? If you are in a credit card fraud situation, right? If you want, high recall, that means you want to find, you don't want to miss anybody, right? Any of the bad ones. That means what will happen? You will also find a lot of good ones fraudulent, right? And then what will happen? People will get upset, right? On the other hand, if you are very this thing and say, oh yeah, no, I'm going to leave everybody out. That means, then what happens? Then the company will get upset at you saying, right? Because a lot of deadbeats would get credit cards and that kind of stuff, right? So that is the precision and the recall. So you have to look at that. So they call it the hit rate, coverage, accuracy, that kind of stuff. Then there are also various other things, the false alarm rate, the specificity. So read through this one because I have covered all the things. So if you see various terms being used, type 1 error, all kind of stuff like that, I have in this diagram, in this slide, I have all the pieces in there. So anyway, the confusion matrix, this is also, there are multiple measures, right? So there is another interesting measure of this one, right? This accuracy. So what is wrong with this accuracy, right? You can just say the TP and TN, the TP plus TN. The things that identified they correctly and they were correct, plus the things that identified as negative and they were negative, divided by the whole number, right? That's accuracy, right? That's a good number, right? That gives you straight accuracy, right? That's what we were doing for example, this might be what they were using in the Kaggle, right? 0.74. So what is wrong with this measure in some sense? So one problem where it gets into is in the healthcare and things like that, right? Predicting cancer, for example. So what is the value of people who get cancer disease, etc.? It's like 0.0 something, right? So if you always predict false, what will happen? You will still be accurate by 99.99% or something like that, right? Right? So that is not good, right? Then you cannot say that, oh, I am 99, but you just have to say everybody, because of that's called the class imbalance, right? Because if there is a class imbalance, then this won't work. So that is why they have other ways of doing it, right? This one will, that one, this F1 will work because it takes the precision and the recall, right? Because so anyway, so just wanted to give you this thing saying that accuracy, just by accuracy is not the right measure for your model. You cannot just say measuring accuracy is my model. So let us look at, so anyway, so going back, the model number 2, let us look at this thing, right? Then the confusion matrix, right? We predicted 99 and 54, right? These are the right ones, and these two are the wrong ones. So if you look at it this way, we know that this is the total number, right? This is 110 and 69. So now the scikit has this thing. It has a classification report. If you give you as the classification report, it will give you this precision, recall, F1 score, etc. Now you know what these things are, right? It will give you all these values. So this is how you can look at, where does this come in the picture when you look at a model? If your precision is high and your recall is low, for example, right? Then you have to put effort into saying that, I am identifying whatever I am identifying are right, but I am not identifying all the right ones, right? So now you have to look at it and say, okay, where did my model go wrong, right? So look at some of the cases and say, okay, give me, so this is why if you draw this one and say, okay, if, for example, this is high, for example, right? You can look at it and say, okay, there is something, I need to look at that, right? On the other hand, if you are identifying everything right, but you are also identifying a lot of the wrong ones, right? Now you have to look at it and say, that's where I should focus by this thing. So this is a good way of evaluating the models. And if you have 2 or 3 models and you can look at it and say, you can look at the F1 score, and then you can compare them and say, yeah, this is the right model for. Does that make sense? Does that clear up at least the context of these things, right? Why do we have these measures, and how do we measure our model, and how can we, how can we make the effectiveness of our model and the predictiveness of our model, that kind of stuff. It depends on the domain space, absolutely.
For example, we're predicting whether the user will like an ad from us.
Mm-hmm.
The cost of him saying him an ad and him not liking it is cheap.
Yep.
Whereas in we want to have we might err on the side of
Yep.
of too many truths. Whereas in the case of will this car explode?
Yep.
In this case,
Yep.
you probably more want to err on the case.
Yep.
Yeah, no, it's not.
Yeah. We might as well change that. What is that ignition key or whatever, ignition, whatever, spring or whatever it is, right? Yeah. Exactly. There is I didn't cover this one. There is also some of the models where you can put the cost of the cost of both sides, right? They're finding it, cost of saying, basically false positives and false negatives and that kind of stuff, right? But what is the cost of finding, that is where they call about the type 1 and the type 2 errors, right? And then you can put the cost in, and then the model will adjust that one. Excellent. Yep. Yes, sir. So anyway, these are the various, so there is this thing that you have an exercise, you can compare the SVM with 4 kernels, for example, right? And you do this one, right? When you get a chance, do this one and then compare them and see what is a better solution, right? Because now that you have all the APIs and everything, it's a lot easier to compare. There is another interesting curve called the receiver operating characteristic. It looks very deep. So let us look at what this thing is all about. So this gives you how good is my model. So this is an interesting one. This is a so what this thing is. This is a true positive rate versus the false positive rate, right? So if you are in F, for example, that is the best situation. You have identified all the positive ones, and you haven't identified any of the negative ones. That's beautiful, right? That is the best. If you are in E is the conservative one, right? Everything is no. Or if you are in H, it is a liberal. Everything is yes. I realize that after the elections and everything, I should keep quiet now, right? Right? We have the elections here about the liberals and all kind of stuff like that. Anyway, it's not a political statement, but the point is, if you so the E and H are interesting, right? This is 0, 0, right? You didn't identify any of the positive ones. You didn't identify any of the negative ones as well. It's good. Here, you identified both of them. You identified the positive ones as well as the negative ones, right? So F is, of course, the ideal, right? You identified all the positive ones, and you didn't identify any of the negative ones. And G, of course, is the worst case, right? You went wrong on both sides, right? So this line, right? This line is a random line, and anything over this, then the northwest, right? The northwest corner is the right curve. If you are here in this one, it's actually a wrong curve. Actually, this is what I was saying. One time I was in a meeting, and the guys were saying, "Oh yeah, we have the ROC curve," and they showed that curve, and the curve was here, nicely here. It was nicely sitting like this. And they were proud of it. Then I said, guys, there is this kind of a tiny problem. I can't go this way. And then they understood what was wrong, right? Because if somebody shows you an ROC curve with the curve going like this on the northeast corner or whatever, southeast corner or whatever it is, it's worse than random. Anyway, so people actually showed. That's why I thought I will put this one in the. So this is not, while I was researching this one, I came up across an example. This is the diagnostic accuracy. This actually is an example, right? They talk about and say less than 0.5, test not useful because it's less than random. 0.5 to 0.6 bad, 0.9 to 0.10. That is the curve under this curve, and that is an excellent one. So people actually use this, right? You plot the ROC curve, the ROC graph, and then find the area under the curve, and then say what graph it is and that kind of stuff. So let us do one thing. We can plot ROC curves as well, right? On our so I have routines here to plot the ROC curve. I'm not going to go through this thing. Oh, guys, we got through this thing, right? 250 to 310 was the. I talked through. We should go in and get some. It's actually 311. I think at least we should get some coffee. Sorry, guys. Sorry. It's a lot easier for me to stand here and do this one. You should point out. My mistake. I should have realized that one. You'll get 10 minutes. Sorry. It was okay, right? I hope it was interesting. Nobody got up, so it is, and nobody looked at the time. So I think it's good. We'll get 10 minutes break, 10, 15 minutes break, and come back. It's okay. I can just keep this one, right? So long as I don't talk anything incriminating, I think I'm okay. Because you might be recording these things. Are you making progress on your updates? Shall we start? Yeah, I work in San Jose, so good guys. Start. Okay, good. We are back. So finally, we had our well-deserving break after this one. Let me just go through the ROC curve. So at least you understood what an ROC curve is, right? And the curve is important. When we evaluate models, we should look at ROC curves. We can evaluate models, different models based on the ROC curves. We will see how. So let us do the ROC curve for our models, right? Yes, so it doesn't have a classifier. That's fine. It doesn't have the classifier somewhere, huh? So let me go up and see. Oh yeah, here. Most probably this is the one that's causing that error. Then first, yeah, this one here. I didn't do this one. See, I didn't do this one. It didn't come, it was all fine then, but when it came here, it got into trouble. It's okay, that's no problem. So when you, see the ROC curve, right? So it plotted the ROC curve. So let us go back and say what it did. It actually plotted the ROC curve for a k-fold validation, right? Remember we were talking about the 5-fold validation. I think it did a 6-fold validation, and then it plotted the ROC curve for a particular decision tree classifier. And so you can see that, the classifiers are okay. This is the luck, right? Remember we are talking about this diagonal, the 0.5, that is the luck. And this is the mean ROC is 0.7, right? The area under the curve. It doesn't, at least we know that it is 0.7, but it doesn't make any sense by itself, right? When it only makes one way is to say that at least we have a 0.7 ROC, but it makes sense only when we compare against something else. But at least you know that how to plot an ROC curve and what does it mean. You can also just plot one single curve, right? If you just want to plot a single curve, you can plot a single curve as well. This is the ROC. Yep, good. It looks good, 0.703. So we know that it works fine. So let me stop at this point. We have the next one is to go for the next one. There are some interesting things on the next competition as well. Before that, I would like to see any questions, anything that you want to see on this one. Anything that you missed, for example, right? If you want to take 10, 15 minutes to go back on any of the things that we covered. You're okay? Yes, sir.
Back when you were talking about the defining of the data, you had one mode was your training data, your test data, and your result data.
Yep.
When do you use result data?
Oh yeah, absolutely. So let me go back to this thing. So you can see it on this one, right? So excellent question. So what happens is, let me go back. So we have a random forest model, and it has multiple parameters, right? So we want to choose the right parameters. So how do we choose the right parameters? Right? Whether it is n equal to 100 works or n is equal to 100,000 works. So in order to do that one, we train using the train set, and then we validate using the validate data set. Right? So we try n equal to 100, you train, you do the validate. Remember we have 3 data sets, right? We have the train, validate, and test. So we put the test in the vault, we don't touch the test at all. We train and validate. So we do train and validate cycle multiple times with different algorithms, with different parameters, etc., etc. At some point, we arrive at the right set of parameters, the right models, etc. Then we bring the test data in, and then apply the test data to that model. And that is the one that gives the accuracy of the model.
Okay, and on the k-fold validation, you're splitting it into like.
Oh yeah. Yep. Yep.
The fifth one doesn't evolve, and then you're training like one, and then test it. You're
Exactly.
validating for
Exactly. See, so now this thing actually the k-fold you can apply to this train and validate, right? And still you have this test data sitting in there. Excellent point. Yep. So you could think of this the test data as the same test data, right? Because the vault is important there. You never want to use the test data for when you do the model. When you do the reason and model, you should never touch the test data. Test data, you put it outside. Don't touch it unless the last minute.
So use that just
before you submit. Usually, for Kaggle, it doesn't matter because Kaggle you can submit multiple times and they will use the best of the time and that kind of stuff. But this is more important when you there is nothing to compare, right? You do this one, the big boss comes in and says, hey, excellent, you have a model. Can you tell me what is your rate, right? What is your success rate? What is your prediction rate?
Is there any, I guess, folklore as far as how you pick what the fault data is? Is it just random
It should be random selection. It should be random selection because if you do the random selection without sampling, right? Usually you don't, it is without replacement. Sorry. So what you do is you have 100,000 records, right? You say okay, 60, 20, 20. You select this 20% randomly out of this 100,000 lines, for example. Take them out, put them into this.
Do you do that? I mean, early at the beginning, we had to clean the data, and
Yep.
like there was some missing columns. One of the fields had a
Imputing and all those things. Yep.
Yeah. Would you do that before you split up the data, though?
Nope. No. Aha. That's an interesting question. It's a very interesting question. Thank you.
Because you get smaller sets than when it comes to the tests.
Yep. No. You will get, yes, you are right. But the thing that happens is when you take a portion of your data as the test data, what happens is you lose that much data for your training, right? Let me put it this way. I forgot. There is an interesting question. I came across somewhere where what these people did was they used the test data as well to do imputing, and then what happened is that actually corrupted the. Yeah, no. You should not. The test data is in the vault. Because if you ever, like for example, like you are saying, like for imputing the data, if you also take the average of the test data, then this thing is gone. That is called data leakage. Unfortunately, I can't recall. In fact, the question was nicely put, and they did all these things. They used this one. They did the imputing and everything. They took the last 20%. They kept it in the vault. They did all these things. Is this the right way of doing it? So what is wrong? And the wrong thing was they used the test data also to do the imputing and other things. Because you should not. You get the data, randomly select 20% of the data, put it in the vault before doing anything. You should not even look at the data because that is. Thank you. Excellent question. Thank you.
What about the case where you have a small minority? So let's say we're doing like a category where we're dealing with people, right?
Yep.
And there's a small minority, let's say it's like 5% population, right?
Yeah. The class imbalance, if there is only. Yeah.
How do we make sure that we avoid the like random picking or something?
There is a yep.
Oh, look, our validation or
Yep.
all our 5% is in the vault data,
Yep.
not in the training data, so we never will learn vice versa.
There are excellent question. Thank you. I haven't done it personally, but there are some techniques. Actually, what you do is in that case you sample. One thing that they do is they take only 5% of the data and then sample. Or there are various techniques that they do. Because if you have a good point there, right? If you sample 99.5 and 0.5, if you sample this 0.5 might never come, or you might take all the 0.5 away. So there are some other techniques where you do selective sampling out of that one. You had a question, or you were?
In fact, there's an R to do that sort of stratified sampling. So that
Stratified sampling. Thank you. Yep. Yeah. Go ahead. Yeah.
so the characteristics of the test data set match with statistics of the training data set. So we have, as close as possible, to 20% men and 80% women survivors in both sides.
Beautiful. Thank you.
So we match those things.
Thank you. Yep. Thank you. Stratified sampling. Thank you. Now I got that. I was wondering the stratified thing, and I didn't get it. Thank you. Now I get it. Yeah, that should reflect the population, the character, the stratification of the data set and the sampling as well. Thank you. Excellent.
Why is the ROC curve a straight line and not a curve?
No, it's a curve, right? It is because we have only two. It depends on the number of points. So if you have got, because it is every point, right? You do multiple iterations, and these are all points. For example, if you do a 6-fold validation, you only get 6 points. It's a curve with multiple points.
I thought every point was one of those curves.
Every point.
Different choice of different k-fold was one of those.
1 point, right? Let me. Thank you. That might be a good question. You are talking about this one, right? Why there are 2 points? Thank you. let me take it under this thing, right? Let me think that through. Most probably because, I have to look at this one and see what it is, but good question. I will take this. Oh yeah, by the way, guys, can you fill this? I think they said you just tick mark the whoever is present. I'll put an answer on this one. Thank you. But I need to think that through and see what does it mean. Anything else? Thanks, guys. So let us go through the next one. Let us go through the next. So we are done with this guy. So let us close and halt. 3. So this is an interesting data set. Let me see whether I have any thoughts on that one. So this is a data science and scikit-learn, right? This is an interesting data set. 342. Finally caught up with the thing. Good. Have you ever seen the A-team, the old A-team? I love it when a plan comes together, right? Anyway, going back, so this is an interesting data set. What they actually did was this data set, right? It is just you have got like 30 or 40. We will look at the data set. You have got like 30 or 40 attributes, and then class 0 and 1, right? It's a class. And the interesting thing is this is actually a simulated data set, right? So when we talk about this thing, there is this property of IID, right? Identical and independent and identically distributed. So interestingly, this thing has that property because it is generated, right? So it has that property. So it's interesting to work with this data because it is IID. Of course, in real life, usually the data won't be IID in that sense. But so that's an interesting thing. Of course, naturally, we will trawl the forums and see what people have done and all kind of stuff. There are a lot of interesting things. There are videos, etc. I have put the links in. So let us go in and see what this means. So yep, this is this thing. I think now I should be bold enough to clear this thing. We start with our imports. So this one has the training data.
Which one did we just open?
3. I think the conference or this thing was in London. The meetup in London. So that is why they say scikit-learn, and I think this was. So you have the data, you have the training data, the training labels, and the test data. Let us look at the training data. It usually helps if we read the data in. See that guy, right? This is just a bunch of numbers, right? It's interesting just to see, just a bunch of numbers, right? It's basically 40 attributes. And if you look at this thing, you see that it's class 1 or 0, right? So for every row, there is like 40 attributes, and at the end they say, okay, whether it is class 0 or 1. The test data is the same story, right? Test data is also 40. They just give you these 40 attributes and say, give me which class they belong. So let us look at the shapes. 1000 data, 1000 by 40, that is the training. And the test data is 9000. So that means they give you data for 1,000 points, and they want us to predict for 9,000 points. Interesting. Anyway, train.y shape, of course, it's 1, right? 1,000 by 1, right? The training data. Does that make sense? So let us do, now that we know things, we have set of features. Let us try our SVC, right? The support vector machine, right? That work, right? Because let us do the support vector machines. So we, create the values, this thing, the RBF kernel, and it gives some errors, but it does what it does. We got this one, right? We got we create this one, we do the fit, we do the predict, we create this thing, and then we do whatever we need to do to create this CSV file and load the CSV file. Right? So let us see how much we get and what does it mean. This is the scikit-learn competitions. This guy. By the way, there are some interesting competitions. I will take a detour for a quick minute. The all-state purchase prediction challenge, that's interesting. Take a look at it. It's the insurance, and it has all kind of strange things in there. The options and how do you, very complex, right? It is not easy. You got to think this through and say, okay, how does it win? How does it pan out? All kind of stuff like that. The Walmart recruiting is interesting. It's a very forecasting, store forecasting. And if you do well, I think they will give you a job. That's the general plan. Oh yeah, absolutely. Guys, Walmart. By the way, they were my customers for my earlier job. So I used to spend days in Arkansas, Bentonville, right? Machine learning, the other one, there were a couple of other things, right? There were a lot of loan prediction, Imperial College London, all kind of things are there, cats and dogs, all kind of interesting things are there. Facebook recruiting was there, data scientist, so C-clicks predict, all kind of interesting, these things are there. The advantage is even if these things are over, right? Each competition has its own nuances to it. The data set is interesting. Now that we can troll the forums and figure out what people did, right, and learn from it. So it's a good exercise by itself. I'm actually whenever you click in Kaggle, just put my name on it, right? Anyway, let us go back here and then let us submit. We shouldn't make a submission. The scikit-learn. Yeah, he also has done 10 on this one because so here we have to go here. Here, notebooks, DSL 1. So this is just a simple 40 features. Put it through a SVM. And see what happens, right? Oh yeah, no, it's already, yeah, I think it got it out. So let me drop it again. And submit. So 91, at least it is 91393, right? And 91262. Right? It's at least it looks good, right? 0.9, so it's like it's not like 0.2 or 0.3. So it's a simple this thing. People have all kind of these things, right? You can see that there are various this thing didn't do me any good. That's okay. So there was this thing, right? There was this warning coming in, right? Something when ID array was expected, change the shape to this one. So let us see what that is all about, right? So anyway, before you submit, we should actually look at and say, make sure that we got what we wanted to submit. We did that one. So if you look at this one, the reason it gave this one was this is what our y was, and it has this double list within a list, right? That is why it was giving. It was expecting a single list. So, which is fine. We change this guy. So what you do is basically you take the 0 dot values, we put that one in, and then we predict, and it works. I just wanted to put this one in so that just to show the manipulation, right? So sometimes you need to manipulate it back and forth. So let us do one thing. Let us do a confusion matrix on this one, right? Remember, now that we know all about model evaluation, etc., we should do the model evaluation. So in order to get the confusion matrix, etc., we should do this 80-20 thing, right? We should, we should do, train a split 80-20. But then we do and then find out the accuracy scores, right? The accuracy is 0.9. I think we got 0.9 something. So I think this is, and if you do the confusion matrix, we know how remember we're talking about this one. So you can draw the see that one, SVM gave a good result, right? That's why we were able to get 0.9, right? It predicted 0, 82, and 98. There were only very little. So the SVM did a good job on this data, right? If we are looking at this one, this is what we should focus on, right? Because we should reduce this number, most probably, right? And then if we reduce this number, I think we'll be home free. So this is where we use the confusion matrix and the various the numbers, right? Precision and recall, etc., to evaluate our model. Does that make sense? Are you comfortable with that? So now, because this one has 40 features, right? We could try some feature learning. We could do some engineering feature stuff, right? Because this was, earlier we had only like 4 or 5 features. It's not easy to do anything. Here we have 40 features. So let us try some interesting things on that. So one of the things that is the PCA. So what it does is, it's a dimensionality reduction technique, right? It looks at the planes with the highest variation, right? And then it does linear combinations of them. So that way, so if you have, what it does is you have 100 attributes, right? And some of them might be correlated. Some of them might have various relationships between them. So there is no meaning in getting all the 100 this thing. And then they also, pollute the models, right? So what it does is this thing goes over this one. It tries to, it does without going into details about the algorithms, it does the matrix, cute math type of stuff, right? It does the matrix, things, that kind of stuff, and it figures out, right? And says, okay, this is a combination that works fine. So let us do a PCA on this data. We do the PCA on this data. So what happens is, and then when we plot, you can see that out of the 39 or 40 variables, only a few of them have the importance, right? What do they call it? The explained variance, right? So this explains the variance, 25% of the variance. This explains 20% of the variance of the data, right? If you look at it, you can say that after about 10, 12, it doesn't matter anymore, right? So instead of 40 attributes, we can actually take 12 attributes. Again, these are not straight attributes. These are the linear combination attributes, right? The PCA attributes. So if we can take 12 of them, and that should give us a better result because the rest of them is just noise. So this is one way of, when you have a lot of attributes, this is one way of reducing the attributes as well as getting to the ones that matter. So let us do this guy. And submit. So it does the sub sub02 file. Let us see. Let's go to Kaggle. Make a submission. This is strange. Something happened. 0.02. So what we did was we did a dimensionality, right? It is not an the reason it didn't improve, right? It didn't improve from my best score, but it did improve from our previous score, I think. Right? Our previous was 0.9. This is like 0.91393. So this is one technique, the PCA, the principal component analysis, is one of the techniques for reducing the dimensionality. When you have a lot of attributes, it is an interesting way of doing that. Does that make sense, guys? Any questions, any suggestions?
So what would be the benefit of reducing the number of dimensions you have? Is this so that your other models you run against it would be faster?
No. There are a few. The first thing is the speed is there, but even more than the speed, if there are a lot of attributes that are not relevant to the model, they will actually increase the error of the model, right? Because the model considers all these things, right? If you have 100 features, and more importantly, if two features are correlated, right? For example, whatever, temperature in degree Fahrenheit and temperature in degree centigrade. This is like a degenerated example, but something like that, right? When you have both of them in there, and when you consider both of them, then your model becomes polluted, right? And so
Part of the idea is you have two that are correlated
into a single one. Yep. It's not a So now first thing that happens is it takes the data of 40 attributes, right? What the PCA does is it looks at it and says, hey, if you look at the attributes, it actually says you put 0.5 of attribute 1 to 0.2 of attribute 2 plus 0.3 of attribute 3, that is one attribute. So it creates synthetic attributes. And then it says, out of the synthetic attributes, these are the ones that are good.
So does that help with the aspect of preferring generalization versus specialization on it? So if you let's say have 10 components,
Yep.
and you go and you say, okay, well, I'm going to do a PCA of 8. Since I'm theoretically losing a little bit of data.
Exactly.
At the noise
Excellent.
level,
Excellent.
more general.
Good point. Yep.
Is that
Yep. You have a good point there. So there is both sides of the coin, right? This thing is that it doesn't take a set of the attributes, but the other side of this thing is maybe those attributes are important in the real life. So there is that component comes in the picture, right? But the reason they do that is when you have a lot of attributes which are related to each other, or which might not be related to the either they have a correlation between each other, or they don't contribute to the performance, whether it is a classifier or a linear regression. And when you have like 1,000 or 5,000 or 10,000 dimensions, there is no way we can figure out which ones are the good ones or which ones are the bad ones, right? So it's not even hundreds, right? When it is thousands or 10,000 of them.
What's a good rule of thumb for when doing PCA, trying to figure out how many components you should have using, or when do you stop adding principal components because it's not giving you any benefit, or I should add components because I'm obviously overcompensating when everything in one component.
Yeah. Yep.
What's sort of a good rule? How would, if you're doing this, how would you go about doing this? Sort of get a good number of components for your data.
You're going to say.
Like 90% is what I've heard. I mean, it's always whatever your model needs, and you just kind of test it out. But I've heard that getting 90% of your variance is usually like a good rule of thumb.
All right.
So when you look at that, if you did like a cumulative sum of variances,
Yeah.
starting at the highest, you get up to 90, and then you say, all right, that's probably.
There is this thing. There is also people sometimes do the cross validation, not you do the validation, right? You do multiple sets, right? You do the multiple set validation and then say which is a number 90, 92, 94, etc. Usually the high 90s are the ones that they take, saying that it explains what it is. By the way, this is the same thing they use for SVD as well, single value decomposition. They do the same when you do the collaborative filtering, etc. Even for single value decomposition, you do a similar this thing, because you get an eigenvector of huge numbers, and then you look at it and say, okay, first 10 or 15 contribute to most of these things, so let me take that one and leave the rest.
When I used to use this way back days ago, what we used it for was the fact that sometimes what you can measure is not necessarily the driving variable, right? So you have a bunch of things, and these are all basically, let's say, formulas based on whatever the actual underlying thing is. And so by doing SVD, you're able to sort of like take these and try and figure out what that single value is driving it. So like you're talking about like ice cream sales, and if you were measuring ice cream sales and crime and doing, if somebody did that before, your actual SVD is actually more like the temperature variable. And you're not actually measuring temperature where your data set, but this is sort of like go.
Yeah. Yeah, good point. Good point. It looks at it and says temperature is the that the value that drives this thing. Excellent point. Good.
We knew what we're looking for that people could measure, but
Yep.
as a general.
As general. Yep. So anyway, I just wanted to. The reason I put this one in was because if you are doing things where there are a lot of attributes, then this is a good way of doing it. And I think I got the right. Yeah. By the way, if you see this percentage PyLab, inline, right? This is where it would have come in. Remember, we were talking about the PyLab, this thing in the IPython notebook, IPyLab equal to inline -- we were putting it when we started the program. Instead of that one, we can put it here like this, and then it will still work as well. This is that magic. They call it the IPython magic. So you can do, there are various percentage IPython magics in there. What I mean is one time, I think I think that is, you know what? I think that, now I know. I think I put PLab in a couple of times and it didn't work. Then I put this one in and it worked. Then I think somewhere else I realized that it's not PLab, it's PyLab, and then I put it back in. At least one mystery solved. So anyway, you can do this one if you want to, there's all of other things. Oh yeah, so here the PCA, the components, right? So now you take the components and transform, and then we predict this one, right? We did this one, and then we can predict this one, and then how it works. So that's all I had on this one, right? Just to the couple of interesting things. One is this is IID, so the data is perfect. In that sense, of course, it's useless, but it is perfect, right? Because it doesn't. It is like what is it, full of sound and fury, signifying nothing type of stuff, right? The Macbeth they talk about, right? Anyway, but it is interesting data in that sense. Interesting data in the sense that it has a lot of attributes, so we can try the PCA and various other things on that. Any thoughts on this one here? Okay. So if we reach up to this one, so let us get this guy out of our way and go back to the last one. Let me go back to my slide set. Anyway, you have the various entries, and then finally the ESUs. This is the PK. It is the Pacific Asia Conference on Knowledge Discovery and Data Mining 2014. This is a very interesting data set. I don't know whether anybody took a look at this data set. Very simple. You have 10 modules, M1 to M10. You have 31 components. I think M1 to M0 to M31, 32 components. They give you the sale date and how much it sold, right? It sold this much on this day, this much on this day, right? The year and month. And they also give you the repairs. when this particular module combination, right, M16, P12 got, sorry, not M16, M8, because more than M is 1 to 10, when the repairs came in. Very simple. You want to predict how much repair, and then they give you the sale data, right? They give you the sale data. You have to predict how much repairs will come for 2 years, 2010 and 2011, for all these modules. Very simple. The data is deceptively simple. There's nothing there, right? Just how many, each month, how much, not each month, whenever it's sold, they give you the sell this thing, and then the repair. That's it. But there are all kind of interesting this thing. That when you look at the data, of course, this is the ASUS this thing. Right? These are actually laptop components. I think the M0 to M10 maybe the 10 of their models or something like that. Right? It's something like that. So they have added all kind of noise to the data. Right? They will not give you the full data. And the second is, so you will see that there are something that have repaired before the sales have happened, and all kind of strange things like that. So you have to figure out all these things. So let us look at, let us troll the forums, of course, right? The forums have all kind of interesting data. There are 2 or 3, I'll go through the data first. First, let us look at the data and then predict some things, right? This is this thing. This is the guy, right? This is the one. So let us take the thing out. Clear this thing out. The data, load the data, right? Repair train, sales train, and output target. Let us look at the data. Like I said, module category, component category, year month, right? They have put the 2007/9, year month sale, repair, number repair, right? This is the repair data. If you look at the sales data, it's more simpler, year, month, and number of sales. That's it, right? And if you look at the what you want to predict, you will see that they have this M1 P02, M2 P02, 2001, month 2, 3, 4. Tell me how many repairs will come. That's all what they have. So one of the interesting things, right? So if you have modules 1 through 10, and component 0 to 31, right? Or 1 to 31. And before that, let us just to get the D types, right? This is the data type. So the minimum is 2010-1, and the max. This is the test data, right? And the maximum 10 is 2011-12, right? So we have 24 months. 24 months. 10 components, 10 modules, 32 components, right? So theoretically, it should be 7440, right? Because you have 10 components, you have the 10 modules, 32 components, and 24 months. But actually, they give you only it's only 4256. So there are some modules are not available, right? No, I'm talking about the test data. Yeah, thank you. The result they wanted. Right? This is this is what. So what they want us to predict is the repairs from 2010-1 to 2011-12. But you have a good point there. We should actually take a look at it and say there is indeed all the months are there. Thank you. That's a good question. I will check. I'm not going to, we can actually do the group by or something like that, and we can look at it and say, but good point, excellent point. It might not be that some month, that will be more interesting, right? Because the interesting thing is, how do we manipulate this data to get this for every combination of the module category for every month? How do you predict that one? So that is that's the interesting part, right? I'm not going to solve it here, but the thing is, think about it, right? So it's a lot more complex. when you look at the data is very simple, but there's a lot more complex things going internally on that one. Does that make sense to you? Anyway, that is that one. So one of the things that we could do, like our earlier ones, right? We can try all ones, right? For every month, right? There is one. We can just put one for every month here, right? Every combination. So that is one we can try. Or all zeros. We can just say no repairs, right? And then see what happens. So this is one of the things that, like we were talking about in the Kaggle, at least for Kaggle competitions, right? Real life, you can't do that one. But for Kaggle competitions, you can actually try these combinations, right? And then see what gives the results. So actually all ones, so if you do the all ones and we submit, right? So we go back here. We go back to the competitions. This is the, oh yeah, maybe we were in the same one. No, sorry. We are in this guy.
So I have a question on the competition. So the ones we're looking at have relatively small data sets, but for example, like the Facebook and some other ones, you have data sets that are like
Gigabyte.
on the order of like 5 to 10 gigabytes that
Yep.
run zip.
Yep.
How do you load them into here to process them? I mean, are there tools you use to cut the data into more manageable pieces to process in series, or?
I haven't, so, usually what I do is, by the time it gets to that one, I put it in I usually have a cluster of machines, 10 machines, so that way you can put it on a cluster of machines and then run them. Usually use Hadoop or that kind of stuff, R Hadoop or etc., and then run them. Second is sometimes I think even on the Facebook one, if I am correct, you can actually do the processing transformation and get the features out.
Yeah, this one was a keyword one, so you could
They reduce the features out. But if the data set, if the processed data set with all the attributes in a table doesn't fit in the memory, then you got to go for distributed processing. There is no other way out on that one.
Distributed processing is not complete, right? You have to write the code differently.
Yeah. I mean, at that point, you have to look at either use MapReduce, for example, right? Use MapReduce. If you use MapReduce even on one, only what will happen is it will process iteratively, right? Even for the same machine, it will do the multiple maps and that kind of stuff.
I think possibly what I was asking also is so here we're using the built-in sort of build me a k-means or whatever kind of thing. Do we have to like hand roll our own for doing parallel, or is there some parallel machine learning code out there on Python that basically we have machines and we can
Let me take that under advisement, right?
at least rephrase it.
Yeah.
Is there stuff that's available to the public? I know stuff that's not.
Yeah, I haven't. By that time, it's usually, you wouldn't use an IPython notebook or something to do that one, right? You got to usually. I also use R and the Hadoop and that kind of stuff, and then look at it in a different way. But your question is valid. How do we, in a Python ecosystem, you can use pandas. There is the scikit-learn models. There are various other things, that will work. But I'm not sure even pandas and scikit-learn models might. But pandas, I don't know whether it will work across multiple machines. Right? It is still a single machine. This thing. Other thing that we can do, is sample from the data set itself. Right?
So you could do like the approach like a random forest one and just build each tree from a random
Yeah.
selection of giant sets.
Yep. Then certain. Yep. Good question. The answer might be an that's not that.
Is there a way to persist the trees? Like the stuff when you do it.
Yeah. There is a way to persist the trees. I think you can pickle the trees.
Okay.
You can even pickle the models if I am correct.
Okay.
Because you can. I haven't done that, but I have seen it somewhere. You can persist the model and then you can load the model back.
If you're using it as sort of a distributed manner, that's the way to persist it, send it
Yeah.
back up on the reduce.
It's a lot more. Even the tree itself has to be right. There are So there are another this thing. The random forest itself, like you were saying, thank you. Good thought. The random forest itself can be parallelized.
Okay.
Because you create the trees and then you process the trees separately. So you can process random forest itself can be processed, can do parallelized. There are linear regression, some of the linear regression can be parallelized. The SVM or a couple of other things they were saying it's difficult to parallelize. We are talking about parallelize when you have a lot more data, right? When you have a lot more samples. And then Mahout, right? That is the Mahout library that uses it's a Java library that uses Hadoop and various other things to process. And there are so of course again I think most of the algorithms that can be parallelized it uses that one, but all algorithms cannot be parallelized and they are not Hadoopable. The one of the things that I am using now that is what I am working on now is the framework called Spark. UC Berkeley Spark. SPARK. UC Berkeley. It's a very interesting this thing. It has got TDD. For the sake I can never keep this thing. Anyway, it takes it into data structures and you can parallelize that one, that kind of stuff. So there are interesting things. But good question. Yep. At that point, you have to think that through. You have to look at the algorithms, etc. It's not as straightforward as just plugging in the algorithms and going forward and doing it.
I was thinking like some of these you get just like
Yep.
start downloading it at the half a day later come back down.
I had so for the earlier one of the things that I was doing was processing Twitter data. And for processing Twitter data, one time, one of my runs took like 19 hours to run it. Right? It was a network, right? You guys do Twitter this thing, the network analysis, right? So you have a million users, and then out of a million users, you have a network, right? You have a network, and then people who follow them, and then you connect the network stuff, and then you do the network graphs, and you find out who is connected to what, all kind of stuff like that. And by the time you do the network processing, it takes a long time. It takes like 19 hours to process one. But time is fine. It's not the time that we are worried about. It's even if it takes more time, that is fine. But if you have more data, then it is a problem, right? If you can't even hold the data, that's where the challenge is.
Whatever that menu framework can take.
Thank you. I should have mentioned that one. Yeah, that's the next thing to do. You go to AWS or Azure and do it. Yeah, first of all, go to the cloud, take a few instances, and then you have this thing to do that one, right? Yeah. At least for parallelizable algorithms, you have a way of doing it.
I was wondering if there's anything that was available sort of out of the box on like the scikit that you could sort of have running in that parallelizable mode.
Yep. Feed the beast the data and it will figure out, right? It will figure out. That's actually a good business idea, most probably.
Well, I know there are a couple of companies that are doing machine learning as a service.
Machine learning,
Basically,
yeah.
approaching
Yep, exactly. You feed the data and yep. Yeah. There are tons of there are a few companies who take your data and they will do that one. By the way, even there are Python, this thing, R, various other machine learning and kind of, yep. Thank you, sir. Now, the only thing is I forgot what I was doing. I was going to submit these things, right? That's what where I was at, I think. I was trying to find out the ASUS this thing and submit this guy. Yep, this guy, and then we will make a submission. Now you can submit as many these things as you want. Yeah, competition is complete, so you are okay. Yep, I think it is O1 or O2, 103, this guy. O2. It's okay. Some error came up, right? The solution was not expected in line 1. Something happened. So anyway, you could have submitted and you could have gotten the result back. I'll go back and so you can do the all ones or all zeros and see. Oh yeah, I think I submitted the wrong data. That's why. I know what happened. This is the wrong. It should be this guy. Notebooks. ASUS. And then, yep, zeros, for example, all zeros, right? That's what we were submitting. So. Yikes, now I have a problem, right? I submitted this all zeros and it's going to do this Kaggle greatness index, right? If it is going to do that one, it should be some interesting algorithm, right? You don't want to do this all zeros. Anyway, I'm just kidding. It's just anyway, it came back like 4.62 or something like that, right? No big deal, right? What we are doing was we are just submitting all zeros, right, and seeing how it is doing, right? Nothing. So then we can do a similar this thing for all ones if we want, right? We can do all ones, and then submit it and then see what happens, right? You'll get so similar. I think we'll get like 5.891 or something like that. The reason I put this one was that's how you start with a new competition comes in. You figure out a few things, right? You figure out all ones, all zeros, something like this, or based on some attribute, based on things, and then say do it, right?
So since you can't submit after competition is closed, is there a way to get the actual answers if you're just trying to use this learning type thing?
So depending on different ones, they do it differently. So sometimes they give you they give you the answer. Okay. Right? They give you the if you go back here, this is what you're asking. Right? They give you this thing and then they give you the rank, right?
Okay.
Right? They give you they give you everything.
But they don't give you the actual answer, like the actual
Yeah. No. Yeah. They never. We could never get the evaluation data. Right? They have the test data that they give you, which we get for an answer. Then they have this evaluation, the final evaluation that we never see. And that is where, if you look at look through some competitions, right? People have lost like 100, 200 ranks on the actual evaluation. So that is where we have to think about the fitting, right? All those things are important, right? You don't want to the overfitting, etc., right? The learning and all those things. You have to be very careful, because what happens is you might get some results on the during the initial this thing, but in the end it will get into trouble. You should see some of the trolls. Some people have lost like rank. They thought that, oh yeah, we did well, and suddenly check like that, this thing goes down by 100. There is also the other side of the story, right? The data might not be as representative of the sample as we thought it would be, right? Selection bias of some sort. Anyway, so now I just wanted to do some transformation, right? We get because we have the YYMM was there, right? So one of the things that we can do is transform the data so that you actually get the year and the month, right? So that you get the you keep on doing. I'm just going to go through and then I'll show you what the final this thing looks like, right? If I could. See, even this one, it takes time because there is like 5,000, some 50,000 or 500,000 or 200,000 or something like some huge number, right? How many data records are there? I never did the shape of this guy, right? The train repair. I think it's like a huge number of records. Anyway, it takes time to transform. In the end, when you transform, you will get things like this, right? You separate the year, separate the month, separate the year, separate the month for the repair and the sales. Right? So now at least we have these things separated. Once we separate these things, we can do, so once you separate all these things, one of the things that happen is I'll show you the types, right? If you look at so the shapes, right? This is 510 records on the train. That's why it takes time. So if you look at the type, these are all object types, the year and the month, etc. So you won't be able to operate on any of them. So we change the type to int64, right? So now you have the types. So all types become. So if you come across the types to be objects or things like that, you can change the types to integers so that you can do the processing. Guys, at least let me know when it is supposed to end. We don't want to sit here for the whole night, right? And so partly we'll be, and I know that we will leave before that, but no, it's not time. Time is there. Anyway, so you can do all these things, and I'm going to. I think this is the best, right? You can do all kind of manipulations. The hint is that here, the things to do are the decay, right? You look at and say how much. First of all, you have to split it into for each modules and category, and you have to split it into this at least 310 splits, right? For each split, you can do the decay. There is a thing called Kaplan-Meier analysis, the Cox model, parametric survival, this thing. These are some of the things that we have to apply for this model, right? To see how many failures happened. Anyway, that is that side of the story. So finally, the beginning is the end, right? We started at some goals. I hope we are able to do enough, right? I will leave it. There are some references, whatever reference I made, and questions. I think we are in good shape. It's 4:30, 4:40 is the time, so I'll leave alone and say questions, thoughts. All kind of stuff in there. So this is the disciplined pursuit of less, right? That's an interesting concept. You do less, and there's a book out and all kind of stuff like that. Any questions, thoughts, comments?
Maybe you gave us 20 or 25 references. How long do you think it takes to go through all of this? Some of them are maybe a 15-minute read little polls. Others are lecture.
Yep.
What should be our expectation to plan our time going to go through all of this?
Easily 6 months. 6 months. 6 to 8 months. Because the Caltech lectures, for example, there are like, right, the Abu Mustafa, they are like 18 lectures, I think, right? 18, they are beautiful lectures. Coursera stuff. These are in-depth stuff, but they are very interesting. The easiest thing is the book by Tipsarani and Hasty, right? That is an easier one. What I wanted to do exactly, thank you for pointing that out, right? I don't know if it's a good or bad. Maybe it's not bad. But the thing is, they wanted to give enough information, right? So that you can do a lot more interesting stuff with data science. Yes, sir.
How do you see machine learning in Python compared with machine learning in R going forward? Both have the good and bad, because I use R all the time. I use Python also all the time, right? So they both have their goods and bads. I like the plyr, dplyr, and that kind of stuff, right? The data.table, all those things are interesting in R. But with the pandas and various other these things, you can do it in Python also. In fact, many times when you do the IPython, you wouldn't know the difference. In the sense that if you think in R terms, right? And then you do it here, you are able to get that one done. So, yeah, go ahead. Yeah.
So if you're used to the R, but you like some of the Python functionality, you can really just...
Beautiful. Good. Thank you. So we can do both. I don't think there is it's preference, right? And the things that you work on more than. I like ggplot, and I haven't seen the ggplot equivalent in IPython that easily yet. It's not that I might not know how to do it, but I can do ggplot a lot easier than the matplotlib and the pylab and that kind of stuff. What are your thoughts? You have been working in R, right? So what do you?
I do both.
Is it?
Whichever is easier today is what I use.
Yeah. But the other thing is also the thinking, right? Sometimes if you know multiple languages, it's difficult to think back and forth, right? You suddenly look at one thing and say, did I see it here or did I see it there, right? And then you have to go back and forth. Anyway, going back, this book is good book, the ISL, right? The Introduction to Statistical Learning. This is a good book, and in fact, it is available free online. Then their bigger book is also interesting. Then Andrew Yang's and then Abu Mustafa's, the Mathematical Monk. I don't know how many of you have seen the Mathematical Monk at YouTube. Oh, that's very good. You have to check. But it's it's thick with mathematical formulas and that kind of stuff. So anyway, it takes time. It takes time, and also you have to think that through. You have to apply these things, right? You have to apply these algorithms at multiple places. That is how you learn about it. That's why I like the Kaggle and the things like that, right? Even today, most probably, we applied many of these algorithms at many places. We looked at them. We understood a few of them. We saw how these things work, right? In the context of data sets. Unfortunately, I don't have the SurveyMonkey, this thing, the link. I got it only today morning, sir.
It's on the tutorials link. You just go to pycon.org.
Yeah, okay.
And click tutorials. It's the very first link.
Okay. So, one of the things they wanted was to. Oh yeah, thank you. One of the things they wanted was to fill in the form, right? This guy. Where is it at? This one. Good. So the tutorial evaluation is there at this thing. At least fill in the evaluation, the good, the bad, and the ugly, right? We have some inside information, so I can manage these things, right? It's not a problem. Anything else? Any suggestion? Was it too much information? Is it? I should have cut the information to half or something like that, or or it wouldn't have worked anyway. At least everybody was able to get to Kaggle and do something with it, right? So that is the first thing that at least if you do that one.
I think the amount of information delivery was good, and I like the fact that you sort of left a lot of information in Reddit for me to dig back into on the slide.
Yeah.
So
Thank you.
means that it wasn't just up.
That's what I would have preferred, and that's why I do it that way, right? The more information.
So how many, it seems like we've talked about classification problems mostly today.
Yep.
Does Kaggle tend to be more on the classification problems than regression?
That's what thank you very much, because I wanted to find a good linear regression problems, but I couldn't find one that is easier. As far as I can tell, a lot of the Kaggle ones are classification problems. There are a few ones where they want to predict the numbers, right? They predict the number of things, so it is there.
Yeah, I remember looking at about a year ago at one that was trying to predict the price of used tractors.
Yeah. Price of that is the price of used tractors. Yeah. The reason, thank you. The excellent point. The reason I did not use that one was they closed that one. We couldn't submit to that one. That was the reason. Otherwise, I wanted to use that one because that was a good one for linear. Thank you. Good point.
And then so if I wanted to practice on a more regression style, should I just read up on the suggestions of the slides?
Yeah, suggestions of the slides, and you can find. I'm sure you can find Kaggle competitions. There are a few. But there might be a lot more the complex data sets, that kind of stuff. But yeah, also if you many of the tutorials, many of the books themselves have, for example, the book by the ESL, the book by Hasty and Tipsarani, they actually have exercises and they have data sets. Thank you. That's a good point. I actually wanted to find a regression one, and I couldn't find one that I can fit in this thing. And I said, fine, let us look at the world from a classification point of view.
What about one thing you didn't cover? I'm not sure it works in Kaggle, but I think is confidence levels and stuff. So like one of the things on like a random forest, right? You might
Yep.
have some trees that are
Yep.
really good in a domain, and so you're basically like if this tree goes down this path, it's not going to have a good match. But if it goes down this path, it's going to have a good match.
Yep.
Is there any stuff? I didn't see anything on the scikit-learn stuff this morning, which was that covered anything about having like multiple models for different parts of for different
Yep.
parts of the domain type stuff.
That's a harder problem to solve, but good, because you should also remember that the ensembles do that one. By the way, the Netflix, thank you, excellent question. The Netflix actually uses remember the Netflix, there was a Netflix competition which they actually gave out like $1 million. It took like 4 years for people they wanted a 10% increase in their recommendation effectiveness. It took like 3 or 4 years for people to do that one. And the team that won the Belcore, I think they did exactly that. They had like 30 or 40 complex models, and then they had this vertical partitioning of the things. Thank you. Good question.
Like other guys who do stock market stuff.
Yeah.
You'll have an ensemble type approach. But,
Yep.
And they do anti-pressure and stuff.
Yep.
One of the things they end up doing is confidence level. So you have a model coming out that says, "Oh, I think it's going to go up, but I'm
Yep.
only like 10% sure."
Yeah.
Ignore me.
Yep. So, yep.
I'm 90% sure it's going to go up.
Yep.
It's like, okay.
Yeah.
But it's only because I recognize this thing exactly.
The IBM Watson. You have seen the Watson this thing, right? What the Watson does is it gives you this thing with the confidence levels. it gives you the confidence level bars for every answer, right? Every question, it gives you. In fact, they show that one. You should watch that, the Watson. You were asking about artificial intelligence, right? You should watch the Watson Jeopardy competition.
Yeah, I saw that one.
Right, and that restores. Remember, first of all, the Jeopardy questions are from various this thing, right? The domains are huge, right? It's like they could ask any kind of questions, and there is satire, there is humor, there are all kind of nuances that only humans understand, right? And then Watson was able to win that one against two champions, but of course it was a in some sense, I shouldn't say this. It's a monstrous atrocity in some sense, in the sense that it's not artificial intelligence. What it did was it went through and it searched with its power, right? And then it came back, and then it had this confidence level. That's not artificial intelligence, right? That's what the machine is good at, and it will do the same thing with the Google, right? Google search, Google Translate. The Google Translate, what it does is it actually looks for the words or something like that in the web and comes back with results. Not that it translates. It doesn't understand the translation. That's what my understanding is. So if an alien comes in, it's good that I am talking about it at the last 2 minutes. So, if an alien comes in and talks to us, Google Translate wouldn't be able to make of it, because nobody has translated it earlier. So anyway, those things are, so anyway, so that's how Watson did its work, right? It did the search and then it got the thing.
Supposed to be reasonably good at their medical aspect of stuff, because it's like they have something's like, well, yes, this is my cancer diagnosis module, which basically most of the time says, I don't know what's going on, ignore me. But then occasionally will say, yes, this is what I want.
And also it is the questions, right? You can say, have you looked at this and that kind of stuff. Instead of predicting and saying, okay, put $1 billion in it, tomorrow the stock market will go up or whatever it is. That requires a very different way of looking at these things.
$2 billion on somewhere where you bet $1 a million times.
$1 million. Yeah. Anything else, guys? We are okay? Going once, going twice, and going twice. Thank you.